The study of exoplanet atmospheres is one of the most exciting and rapidly advancing frontiers in our ongoing quest to find life beyond Earth. When we look out at the vast, star-dusted canvas of the night sky, we are no longer just seeing points of light. We are beginning to see other worlds, other potential homes for life, each with its own unique story, a story that is largely written in the thin, gaseous envelope that surrounds it. Scientists analyze the composition and the characteristics of these distant worlds, searching for the telltale chemical fingerprints that could indicate the presence of a living biosphere. One of the primary focuses of this search is the presence of certain key gases, oxygen, methane, and carbon dioxide, which, on our own planet, are deeply and inextricably linked to the processes of life. The detection of a significant amount of free oxygen in an exoplanet's atmosphere, for example, would be a discovery of immense importance. Oxygen is a highly reactive gas. On geological timescales, it should not exist in a free state in a planet's atmosphere unless it is being constantly replenished. On Earth, the primary source of this replenishment is photosynthesis, the process by which plants and algae use sunlight to convert carbon dioxide and water into energy, releasing oxygen as a byproduct. Finding a similar oxygen-rich atmosphere on a distant world would be a powerful, though not definitive, piece of evidence that a similar to planet-scale biological process might be at work. But the story is often more subtle and more complex than the search for a single gas. The balance of different gases can be an even more powerful biosignature. The simultaneous presence of both oxygen and methane in significant quantities, for example, is a strong indicator of biological activity. These two gases are in a state of chemical disequilibrium. They should rapidly react with each other and be removed from the atmosphere. On Earth, the only reason they coexist is because they are both being constantly produced by life oxygen by photosynthesis and methane by microbial metabolism. Finding this specific, unstable chemical cocktail on another world would be a profound and tantalizing clue. To peer into these distant atmospheres, scientists use a new generation of incredibly powerful telescopes, like the James Webb Space Telescope. Using a technique called transmission spectroscopy, they can analyze the faint starlight that filters through a planet's atmosphere as it passes in front of its host star. Different gases absorb light at different, specific wavelengths, leaving a unique chemical barcode imprinted on the starlight. By deciphering this barcode, we can determine the composition of the atmosphere, its temperature, its pressure, and we can even begin to infer the presence of clouds and weather patterns. All of these are crucial pieces of the puzzle of habitability, a puzzle that we are, for the first time in human history, beginning to assemble. An exoplanet, or an extrasolar planet, is simply a planet that orbits a star outside of our own solar system. For most of human history, the existence of such worlds was a matter of pure philosophical speculation, but in the last 3 decades, thanks to a revolution in our observational capabilities, we have moved from a state of knowing of 0 exoplanets to a state of knowing of over 5,000 confirmed worlds, with thousands more candidates waiting in the wings. The discovery of this vast and diverse galactic population of planets has been one of the most profound and transformative discoveries in the history of astronomy. It has shown us that planets are not a rare or a special phenomenon, but are a common, and perhaps even ubiquitous, byproduct of the process of star formation. The galaxy, it seems, is teeming with worlds. To find these distant, and often very faint, celestial bodies, astronomers have had to develop a number of ingenious and often indirect detection techniques. The most prolific of these has been the transit method. This technique relies on the chance alignment of a planetary system with our line of sight. If a planet's orbit happens to carry it directly in front of its host star, it will block a tiny fraction of the star's light, causing a small periodic dip in its brightness. Space telescopes like Kepler and TESS have been designed to stare at large fields of stars for long periods of time, monitoring their brightness with incredible precision, searching for these telltale transit signals. By measuring the depth of the dip, we can determine the size of the planet. By measuring the time between dips, we can determine its orbital period. Another powerful technique is the radial velocity or Doppler spectroscopy method. An orbiting planet does not just revolve around its star. The two objects orbit their common center of mass. This means that as the planet orbits, it causes its host star to wobble slightly. This wobble is too small to be seen directly, but it can be detected in the star's light spectrum. As the star wobbles towards us, its light is slightly blue shifted. As it wobbles away, it is slightly red shifted. By measuring these tiny periodic shifts in the star's spectral lines, we can infer the presence of an orbiting planet and, crucially, we can determine its minimum mass. A more challenging, but incredibly exciting technique is direct imaging. This is the holy grail of exoplanet science, to actually take a picture of the planet itself. This is an incredibly difficult task, as the planet is typically 1 billion times fainter than its host star and is separated from it by a tiny angle on the sky. It is like trying to see a firefly next to a searchlight from a distance of thousands of miles, but with the help of sophisticated techniques like adaptive optics, which can correct for the blurring effects of the Earth's atmosphere, and coronagraphy, which uses a small physical mask to block out the overwhelming light of the star. We are now, for the first time, beginning to directly image some of the largest and most distant exoplanets. The combination of these different techniques is incredibly powerful. If we can measure a planet's size from a transit and its mass from the radial velocity method, we can calculate its density, which gives us a crucial clue about its composition. Is it a rocky, Earth-like world or a puffy gas giant like Jupiter? As our technology continues to advance, as our telescopes become larger and our instruments more sensitive, we are moving into a new era of exoplanet science. An era where we are no longer just detecting these worlds, but are beginning to truly characterize them, to study their atmospheres, to search for the signs of habitability, and to perhaps, one day, find the definitive evidence that we are not alone in the universe. The atmosphere of an exoplanet is the key that can unlock the secrets of its nature, its history, and its potential to harbor life. It is a thin, fragile, and often complex layer of gas that acts as the crucial interface between the planet's surface and the wider cosmic environment, like the atmosphere of our own Earth. An exoplanet's atmosphere acts as a protective blanket, shielding the surface from the harsh radiation of its host star and from the constant rain of micrometeoroids from space. It also acts as a global thermal regulator, trapping heat through the greenhouse effect and transporting it from the planet's warm equatorial regions to its colder poles, creating a more stable and more equitable global climate. Without this atmospheric blanket, a planet's surface would be subject to wild and often life-prohibiting temperature swings between day and night. By studying the composition of an exoplanet's atmosphere, we can begin to piece together the story of its geological and, perhaps, its biological history. The presence of gases like carbon dioxide and sulfur dioxide can be a sign of active volcanism, a process that can release crucial, life-sustaining nutrients and can help to replenish a planet's atmosphere over geological timescales. The presence of oxygen and methane, as we have seen, can be a powerful, though not definitive, indicator of biological activity. These biosignature gases, when found together in a state of chemical disequilibrium, are a tantalizing hint that a planet-scale, living biosphere may be at work, constantly shaping and maintaining the chemical composition of its own atmosphere. To decipher the chemical code of these distant atmospheres, astronomers primarily use the technique of transit spectroscopy. When a planet passes in front of its host star, a small fraction of the starlight is filtered through the planet's atmosphere. Different gases in the atmosphere absorb light at specific, characteristic wavelengths, leaving a unique absorption fingerprint imprinted on the star's spectrum. By carefully analyzing these tiny absorption features, we can determine which gases are present in the atmosphere and in what quantities. We can also learn about the atmosphere's temperature and pressure structure, and even about the presence of clouds or hazes. The study of exoplanet atmospheres is also a journey into a vast and unexplored territory of planetary evolution. Why does a planet like Venus have a thick, runaway greenhouse atmosphere, while a planet like Mars has a thin, cold, and almost non-existent one? The answer likely lies in a complex interplay of factors: the planet's initial composition, its distance from its star, the presence or absence of a protective magnetic field, its history of volcanic activity and asteroid impacts. By studying the atmospheres of a wide and diverse range of exoplanets, we can begin to understand the different evolutionary pathways that a planet can take. We can start to build a more general and more powerful theory of planet formation and evolution. A theory that can help us to understand not just the worlds out there, but also the long and often contingent history of our own precious and life-bearing planet. The art of studying the faint, ghostly light from the atmospheres of distant exoplanets is a field that is pushing the very limits of our observational technology and our analytical ingenuity. One of the most powerful and widely used techniques is transit photometry, which, as we have seen, measures the tiny dip in a star's light as an orbiting planet passes in front of it. While this primarily gives us the size of the planet, it can also provide our first crucial clues about its atmosphere. A planet with a thick, puffy, hydrogen-rich atmosphere will appear slightly larger during a transit than a rocky or airless world of the same mass, as its extended atmosphere will block a bit more of the starlight. By measuring the size of a transiting planet at different wavelengths of light, we can begin to build a crude spectrum of its atmosphere, a technique known as transmission spectroscopy. This is the primary method that is being used by the James Webb Space Telescope to study the composition of exoplanet atmospheres. During a transit, the telescope's incredibly sensitive spectrographs can measure the tiny, additional amount of starlight that is absorbed by the planet's atmosphere at hundreds of different infrared wavelengths simultaneously. This allows us to search for the characteristic absorption features of a wide range of different molecules, from the simple, like water vapor and carbon dioxide, to the more complex and potentially life-indicating, like methane and ozone. Another complementary technique is emission spectroscopy, which is used to study the light that is emitted by the planet itself. This is often done during a secondary eclipse, the moment when the planet passes behind its host star. Just before the planet disappears, we are seeing the combined light of the star and the day side of the planet. When the planet is hidden, we are seeing the light of the star alone. By subtracting the second measurement from the first, we can isolate the faint, thermal, infrared emission of the planet's day side. The spectrum of this emission gives us a direct measurement of the planet's temperature and the composition of its upper atmosphere. This is a particularly powerful technique for studying the hot, tidally locked hot Jupiters, as their day sides are often glowing at thousands of degrees. For the more challenging task of studying the cooler and much fainter Earth-like planets, we will likely need to rely on the technique of direct imaging. This is an incredibly difficult, but ultimately more powerful method. By using a combination of a large telescope, a sophisticated adaptive optics system to correct for the blurring of the Earth's atmosphere, and a coronagraph to block out the overwhelming glare of the host star, we can, in principle, take a direct picture of the planet itself. We can then pass the faint, reflected light from the planet through a spectrograph to analyze its atmosphere. This is the holy grail of exoplanet science, as it would allow us to study a much wider range of planets, not just the ones that happen to transit, It would also allow us to search for the signs of surface features, like oceans and continents, by looking for the subtle, periodic variations in the planet's reflected light as it rotates. While direct imaging of a true, Earth-like planet is still beyond the reach of our current ground-based telescopes, it is one of the primary long-term scientific goals for the next generation of extremely large 30-meter class telescopes that are now under construction, and NASA is now in the early stages of designing a future large, space-based telescope, a successor to Hubble and Webb. That would be specifically designed and optimized for the direct imaging and the spectroscopic characterization of dozens of potentially habitable, Earth-like worlds orbiting the nearest stars. This is a multi-decade and profoundly ambitious project, but it is one that holds the promise of finally and definitively answering the question of whether we are alone in the universe. To determine the precise chemical composition of an exoplanet's atmosphere, scientists must become masters of the art of spectroscopy, the science of deciphering the hidden chemical information that is encoded in light. Every atom and every molecule has a unique and characteristic set of energy levels that its electrons can occupy. When a photon of light with just the right amount of energy, just the right wavelength or color hits an atom or a molecule, it can be absorbed, kicking an electron up to a higher energy level. This process leaves a dark absorption line in the spectrum of the light. Conversely, when an excited atom or molecule relaxes, its electron can drop back down to a lower energy level, emitting a photon of a specific energy, creating a bright emission line in the spectrum. This set of absorption and emission lines is a unique and absolutely reliable fingerprint for a particular chemical species. By passing the light from a distant star or a planet through a spectrograph, a device that splits the light into its constituent wavelengths, we can read these chemical fingerprints and determine which elements and which molecules are present. In the context of exoplanet atmospheres, the primary technique is transmission spectroscopy, which we use for transiting planets as the starlight filters through the planet's atmosphere. The different gases present will absorb the light at their own characteristic wavelengths. By comparing the spectrum of the star when the planet is in front of it to the spectrum when it is not, we can isolate the tiny absorption signature of the planet's atmosphere itself. This is an incredibly challenging measurement, as the atmospheric signal is often only a tiny fraction, a few parts per million of the total starlight. It requires a telescope with a large, light-gathering mirror and a very stable and sensitive spectrograph. The James Webb Space Telescope, with its massive 6.5-meter primary mirror and its suite of powerful infrared spectrographs, is a machine that has been specifically designed and optimized for this very task. It is capable of detecting the faint absorption signatures of a wide range of molecules that are crucial in the search for life, including water vapor, carbon dioxide, methane, and ozone. Another powerful technique is thermal emission spectroscopy, which we use to study the infrared light that is emitted by the planet itself. This is particularly effective for hot gas giant exoplanets, which are often glowing brightly in the infrared. The spectrum of this emitted light can tell us about the temperature of the planet's atmosphere and the presence of molecules that are absorbing and re-radiating heat, like water and carbon monoxide. This allows us to build a temperature-pressure profile of the atmosphere, to understand how its temperature changes with altitude. The ultimate goal of this spectroscopic exploration is to build a comprehensive chemical inventory of a diverse range of exoplanet atmospheres. By comparing the chemical compositions of different types of planets, the rocky super-Earths, the gaseous mini-Neptunes, the giant hot Jupiters, we can begin to understand the different chemical and physical processes that shape their atmospheres. We can test our theories of planet formation and evolution. And, most excitingly, we can search for the subtle and potentially life-indicating chemical anomalies, the biosignatures. That could be the first, tantalizing hint that we have finally found a world that is not just habitable, but is, in fact, inhabited. A biosignature is a feature, a substance, a pattern, a process whose presence is a potential indicator of life. The search for biosignatures in the atmospheres of distant exoplanets is one of the most exciting and challenging frontiers in modern science. It is a quest that is not just about finding a single, smoking gun molecule, but about building a comprehensive and statistically robust case for the presence of a living biosphere. One of the most sought-after and most powerful potential biosignatures is the presence of a significant amount of free molecular oxygen in a planet's atmosphere. As we have seen, oxygen is a highly reactive gas, and it should not exist in a free state for long unless it is being constantly replenished. On Earth, the source of this replenishment is photosynthesis. Finding a similar oxygen-rich atmosphere on a rocky, temperate exoplanet would be an incredibly exciting discovery, but it would not, in itself, be definitive proof of life. There are known abiotic processes that could, in principle, produce a significant amount of oxygen in a planet's atmosphere. For example, the intense ultraviolet radiation from a host star could split water vapor molecules into hydrogen and oxygen, a process called photodissociation. If the planet's gravity is too weak to hold on to the light, fast-moving hydrogen atoms, they can escape into space, leaving the heavier oxygen atoms behind. This could, over geological time, lead to a significant buildup of oxygen in the atmosphere of a planet that is completely devoid of life. This is why the context is so important. The detection of oxygen becomes a much more compelling biosignature when it is found in combination with a reducing gas like methane. The simultaneous presence of these two, chemically incompatible, gases is a strong indicator of a planetary scale, chemical disequilibrium, a state that is very difficult to maintain without a powerful and continuous biological source for both. This is the redox biosignature, and it is one of the primary targets for telescopes like the James Webb Space Telescope. But our search for biosignatures must not be too Earth-centric. Life on other worlds could be very different from life on Earth, with a different biochemistry, a different metabolism, a different set of atmospheric byproducts. This is why scientists are also developing a suite of agnostic biosignatures, indicators that are not tied to a specific terrestrial biochemistry. This could include the search for a general, planetary-scale chemical disequilibrium, the presence of an unexpected and complex mixture of gases that cannot be explained by any known geological or photochemical process. It could also include the search for complex and information-rich organic molecules, or for a specific and unusual isotopic ratio in a gas like carbon dioxide, which could be a sign of a metabolic process that preferentially uses one isotope over another. The detection and the confirmation of a true biosignature will likely not be a single eureka moment. It will be a long, slow, and painstaking process of gathering evidence, of ruling out all possible abiotic explanations, of building a cumulative and statistically robust case. It will require observations from multiple different telescopes, at multiple different wavelengths, over multiple different times. It will require a deep and deeply interdisciplinary collaboration between astronomers, planetary scientists, chemists, biologists, and statisticians. But it is a process that is now, for the first time in human history, finally underway. And it is a process that holds the promise of a discovery that would forever change our understanding of our place in the universe. The presence of water vapor in the atmosphere of an exoplanet is one of the first and most crucial clues in our assessment of its potential habitability. Water is, as far as we know, the universal solvent for life, the liquid medium in which the complex chemical reactions of biology can take place. All life on Earth, from the simplest microbe to the most complex animal, is fundamentally dependent on liquid water. And so, the search for habitable worlds is, In its first approximation, a search for worlds that have the right conditions for liquid water to exist on their surface. The presence of water vapor in a planet's atmosphere is a powerful and often the only indicator that such conditions might exist. It suggests that there is a reservoir of water on the planet, either in the form of surface oceans, lakes, and rivers, or perhaps in the form of subsurface aquifers or ice deposits. And it suggests that the planet's surface temperature is, at least in some places and at some times, above the freezing point of water. To detect this water vapor, astronomers use the technique of transmission spectroscopy. As the starlight filters through the planet's atmosphere during a transit, the water vapor molecules will absorb the light at a number of specific and well-known infrared wavelengths. The James Webb Space Telescope, with its incredible sensitivity in the infrared, is a machine that is perfectly tuned to detect these subtle water absorption features, and it has already been stunningly successful, detecting the unambiguous signature of water vapor in the atmospheres of a number of different exoplanets, from the hot, puffy gas giants to the smaller and potentially rocky super-Earths. But the mere presence of water vapor is not, in itself, enough to confirm that a planet is habitable. The context is crucial. A planet could have a significant amount of water vapor in its upper atmosphere, but its surface could be far too hot for liquid water to exist. A steam world with a runaway greenhouse effect, like a more extreme version of Venus. Or a planet could have a surface that is completely frozen, with a very thin atmosphere that contains a small amount of water vapor that has sublimated from the surface ice. To distinguish between these different scenarios, we need to combine the detection of water vapor with other information. We need to know the planet's temperature, which we can estimate from the brightness of its host star and its orbital distance. We need to know about the presence of other greenhouse gases, like carbon dioxide, which can help to keep the planet warm. And we need to know the planet's mass and size, which can tell us about its density and its ability to hold on to its atmosphere. By putting all these pieces of the puzzle together, by building a comprehensive and self-consistent model of the planet's atmosphere and climate, we can begin to build a more confident case for the potential existence of a stable, liquid water ocean on its surface. The search for water vapor in the atmospheres of exoplanets is a crucial and deeply exciting first step in our long and challenging quest to find another living world. It is the search for the single, most essential ingredient for life as we know it. A search that is now, for the first time, finally, within our technological grasp. Greenhouse gases, the atmospheric components that are so often vilified in the context of our own planet's changing climate, are, in a more general, cosmic context, one of the essential ingredients for planetary habitability. The greenhouse effect is the process by which certain gases in a planet's atmosphere, like carbon dioxide, methane, and water vapor, trap a portion of the infrared thermal radiation that is emitted from the planet's surface, preventing it from escaping directly into space. This trapped heat warms the lower atmosphere and the surface, creating a more stable and more temperate global climate. Without the natural greenhouse effect, the Earth's average surface temperature would be a frigid and life-prohibiting -18 degrees Celsius, and our oceans would be frozen solid. The greenhouse effect, then, is what makes our own planet a habitable, Goldilocks world, not too hot and not too cold. And the same principle applies to exoplanets. The habitable zone around a star is traditionally defined as the region where a rocky planet with a thin atmosphere could maintain liquid water on its surface. But this is a simplistic definition. The true habitability of a planet depends critically on the composition and the thickness of its atmosphere, and in particular on the strength of its greenhouse effect. A planet that is on the outer, colder edge of the habitable zone could still be warm enough for liquid water if it has a thick, carbon dioxide-rich atmosphere that can provide a powerful, warming greenhouse blanket. This is the faint young sun paradox in our own solar system's history. 4 billion years ago, the Sun was about 30% fainter than it is today, and the Earth should have been a frozen snowball. The reason it was not is that the early Earth's atmosphere likely had a much higher concentration of greenhouse gases, like carbon dioxide and methane, which kept the planet warm enough for the first life to emerge in its liquid water oceans. Conversely, a planet that is on the inner, hotter edge of the habitable zone could be pushed into a runaway greenhouse state if its atmosphere is too thick or too rich in water vapor. This is what is thought to have happened to Venus. As the planet warmed, its oceans began to evaporate, putting more water vapor, a powerful greenhouse gas, into the atmosphere. This led to more warming, which led to more evaporation, in a catastrophic positive feedback loop that eventually boiled away the planet's oceans and left it with the thick, hot, and crushingly dense carbon dioxide atmosphere that we see today. The study of the greenhouse effect on exoplanets is, therefore, a crucial part of our assessment of their potential habitability. By using telescopes like the James Webb Space Telescope to measure the concentrations of greenhouse gases in their atmospheres, we can begin to build more sophisticated climate models for these distant worlds. We can start to understand the delicate, and often complex, balance of forces that determines whether a planet will be a temperate, watery haven like the Earth, a frozen ice ball like the early Mars, or a scorching, runaway greenhouse hellscape like Venus. And in doing so, we will not only be searching for other habitable worlds, we will also be gaining a deeper and more profound understanding of the precious and perhaps precarious climatic balance of our own beautiful and life-bearing home. The detection of free molecular oxygen in the atmosphere of a rocky, temperate exoplanet would be, without a doubt, one of the most exciting and potentially revolutionary discoveries in the history of science. It is a discovery that is often considered to be the holy grail of the search for extraterrestrial life. A tantalizing, though not yet definitive, hint that a planet scale, and powerfully transformative. Biological process may be at work on another world. The reason that oxygen is such a compelling biosignature is that it is a highly reactive and chemically unstable gas. In a planetary atmosphere, oxygen will readily react with the rocks on the surface, a process called oxidation, and it will also react with other gases in the atmosphere, like methane. This means that, in the absence of a powerful and continuous source, any free oxygen in a planet's atmosphere should be rapidly removed on geological timescales. On Earth, the only reason we have a stable, 21% oxygen atmosphere is because of a single, and profoundly revolutionary, biological innovation, oxygenic photosynthesis. This is the process by which plants, algae, and cyanobacteria use the energy of sunlight to split water molecules, releasing oxygen as a waste product. For the first 2 billion years of Earth's history, life was purely microbial and anaerobic, and the atmosphere was almost completely devoid of oxygen. But then, about 2.5 billion years ago, a new kind of bacterium, the cyanobacteria, evolved the ability to perform oxygenic photosynthesis. This led to the Great Oxidation Event, a period where the oxygen produced by these tiny microscopic organisms began to build up in the atmosphere, fundamentally and irrevocably transforming the entire planet. It was an event that was likely a mass extinction for the anaerobic life forms that had dominated the early Earth. But it was also an event that paved the way for the evolution of all the complex, oxygen-breathing life, including ourselves, that we see today. So, when we look for oxygen in the atmosphere of an exoplanet, we are, in a very real sense, looking for the potential signature of another Great Oxidation Event. Another moment in cosmic history where life has fundamentally and powerfully reshaped its own planetary home. But, as with all biosignatures, the context is crucial. There are known Abiotic ways to produce oxygen. The photodissociation of water vapor by ultraviolet light is one such mechanism. A runaway greenhouse effect, like the one that may have occurred on Venus, could also lead to a massive buildup of oxygen in a planet's atmosphere after all the water has been boiled away and the hydrogen has escaped to space. This is why the detection of oxygen must be accompanied by a comprehensive characterization of the entire planetary system. We need to look for the presence of other reducing gases, like methane, which would create a powerful chemical disequilibrium. We need to understand the properties of the host star, to see if its ultraviolet flux is high enough to drive a significant abiotic oxygen production. And we need to have a good estimate of the planet's mass and size to see if its gravity is weak enough to allow for the preferential escape of hydrogen. The search for oxygen is a complex and deeply interdisciplinary puzzle. It is a puzzle that we are now, for the first time, beginning to have the tools to solve. And it is a puzzle whose solution could, one day, provide us with the first, tantalizing, and truly profound piece of evidence that the story of life is not a story that has been told only once, on our own, small and very special pale blue dot. Methane, a simple and often overlooked molecule, has become one of the most intriguing and hotly debated players in our ongoing search for life beyond Earth. On our own planet, methane is a gas that is overwhelmingly associated with biological activity. It is produced by a class of ancient anaerobic microorganisms called methanogens, which thrive in oxygen-poor environments like wetlands, the digestive tracts of animals, and the deep ocean floor. This deep and intimate connection between methane and life is what makes it such a compelling potential biosignature. The detection of methane in the atmosphere of Mars, for example, has been a source of immense excitement and scientific controversy for years. The methane on Mars appears to be present in very small quantities, and it seems to vary both seasonally and geographically. This could be a sign of active, subsurface microbial life, with the microbes releasing methane in the warmer summer months. But it could also be the result of a purely geological, abiotic process, like the interaction of water with certain kinds of rocks, a process called serpentinization. Distinguishing between these two possibilities is one of the primary scientific goals of missions, like the Perseverance rover. In the context of exoplanet atmospheres, the detection of methane becomes an even more powerful biosignature when it is found in the presence of oxygen. As we have seen, these two gases should not coexist in a state of chemical equilibrium. Finding them together in a rocky, temperate world's atmosphere would be a strong indication that a powerful, planet-scale biosphere is at work, constantly producing both. But even on its own, methane can be a tantalizing clue. The James Webb Space Telescope has already detected the signature of methane in the atmospheres of a number of different exoplanets. In most of these cases, these are hot, gas giant planets where the methane is likely produced by high-temperature, equilibrium chemistry in their deep atmospheres. But the holy grail is to detect methane in the atmosphere of a small, rocky, and potentially habitable world. Such a detection would immediately trigger a host of follow-up observations and a flurry of theoretical modeling, as scientists would try to determine if the methane could be explained by any plausible abiotic source, like volcanism or impacts from comets. If all the known, non-biological explanations fail, then the possibility of a biological origin of a planet that is breathing methane would become a very real and very exciting. 1. The story of methane is a beautiful example of the subtle and often ambiguous nature of the search for life. It is a story that requires us to be both open-minded and deeply skeptical, to be both creative in our hypothesis building and rigorous in our data analysis. And it is a story that is a powerful reminder that the universe is a complex and often surprising place. A place where the same simple molecule can be a sign of something as mundane as a rock reacting with water, or something as profound and as wonderful as the first, faint chemical whisper of an alien life. The temperature and the pressure of an exoplanet's atmosphere are two of the most fundamental parameters that determine its potential habitability. They are the master variables that control the physical state of water, the rates of chemical reactions, and the overall global climate of a world. On Earth, the delicate and fortunate combination of our atmospheric pressure and our surface temperature is what allows for the existence of stable, liquid water oceans, a feature that is thought to be essential for the origin and the evolution of complex life. The pressure of our atmosphere at sea level, about 1 bar, is just right to keep water from boiling away at our planet's average temperature. And our average global temperature of about 15 degrees Celsius is a product of the delicate balance between the incoming energy from the sun and the warming greenhouse effect of our atmosphere. When we look out at our neighboring planets, we see what happens when this delicate balance is not met. Venus, with its crushingly thick 90-bar atmosphere, has a runaway greenhouse effect that has created a surface temperature of over 450 degrees Celsius, hot enough to melt lead. Mars, on the other hand, with its thin, less than 1% of an Earth atmosphere, has a very weak greenhouse effect, and its average surface temperature is a frigid -63 degrees Celsius. On Mars, liquid water can only exist for brief periods in a few localized areas, before it either freezes or boils away in the low-pressure environment. The study of the temperature and the pressure conditions on exoplanets is, therefore, a crucial part of our assessment of their potential to harbor life. To estimate the temperature of an exoplanet, we can start with a simple calculation based on the brightness of its host star, its distance from the star, and its albedo, or reflectivity. This gives us the planet's equilibrium temperature, the temperature it would have if it had no atmosphere. But the true surface temperature can be very different, depending on the strength of its atmospheric greenhouse effect. To probe this, we can use the technique of emission spectroscopy. By measuring the infrared, thermal radiation that is emitted by the planet, we can get a direct measurement of the temperature of its upper atmosphere. And by comparing this with the predictions of our climate models, we can begin to infer the properties of the lower atmosphere and the surface. The pressure of an exoplanet's atmosphere is more difficult to measure directly, but we can get clues from the shape and the width of the spectral absorption lines in its transmission spectrum. A thicker, higher pressure atmosphere will produce broader, more pronounced absorption features. We can also use the planet's mass and radius to calculate its surface gravity, which in turn influences its ability to hold on to a thick atmosphere. The ultimate goal of this research is to find a true Earth-like analog, a rocky, temperate planet with a 1-bar nitrogen-oxygen atmosphere and a stable, liquid water ocean. This is a search that is on the very edge of our current technological capabilities. But it is a search that is being driven forward by a new generation of powerful telescopes and a new, more sophisticated understanding of the complex interplay between a planet's geology, its atmosphere, and its climate. And it is a search that is a powerful reminder of the incredible, and perhaps rare, good fortune of our own planetary home, a world where the temperature and the pressure are for us just right. The chemical composition of an exoplanet's atmosphere is a rich and complex tapestry, a story that is written in the language of spectral lines. To read this story, to decipher the chemical code of these distant worlds, scientists have developed a sophisticated and powerful toolkit of spectroscopic techniques. The workhorse of this field is transmission spectroscopy, TSI, a method that is used to study the atmospheres of transiting exoplanets. As the planet passes in front of its host star, a tiny fraction of the starlight is filtered through the upper layers of the planet's atmosphere. The different atoms and molecules in the atmosphere will absorb the starlight at their own, unique and characteristic wavelengths, leaving a set of dark absorption lines imprinted on the star's spectrum. By carefully measuring the depth and the position of these lines, we can identify which gases are present in the atmosphere. and in what quantities. This is a technique that is particularly powerful in the infrared part of the spectrum, where many of the most important and potentially life-indicating molecules, like water, carbon dioxide, and methane, have their strongest absorption features. This is why the James Webb Space Telescope, with its incredible sensitivity in the infrared, is a true game-changer for the field of transmission spectroscopy. Another, and complementary, technique is emission spectroscopy. This method is used to study the light that is emitted by the planet itself. It is most effective for hot exoplanets, which are glowing brightly in the infrared. By passing this emitted light through a spectrograph, we can search for the bright emission lines that are produced by the hot gases in the planet's atmosphere. This technique can give us a direct measurement of the planet's temperature and the chemical composition of its day side, the side that is permanently facing the star. By observing the planet at different points in its orbit, as different parts of its surface rotate into view, we can even begin to build a crude, two-dimensional map of the planet's temperature and atmospheric composition, a technique called eclipse mapping. This allows us to study the planet's global climate, to look for the presence of clouds, and to understand how heat is transported from the hot day side to the cold night side, for the more challenging task of studying the cooler and much fainter Earth-like planets. We will likely need to rely on the technique of high-resolution spectroscopy combined with direct imaging. A high-resolution spectrograph is an instrument that can split the light into a very large number of very narrow wavelength channels. This allows us to resolve the individual, rotational, and vibrational lines of a molecule, providing a much more definitive and unambiguous detection. It also allows us to use the Doppler shift of these lines to measure the wind speeds in the planet's atmosphere, and even to detect the subtle, seasonal changes in the atmospheric composition that could be a sign of a living, breathing biosphere. The toolbox of the exoplanet spectroscopist is a rich and a powerful one. And as our telescopes become larger, as our spectrographs become more sensitive, and as our analytical techniques become more sophisticated, we are moving into a new and exciting era. An era where we will be able to move beyond just detecting these distant worlds and will be able to truly characterize them, to read their chemical stories, and to perhaps, one day, find the one special story that tells us that we are not alone. The distance of an exoplanet from its host star is one of the most critical factors that determines the nature and the evolution of its atmosphere. It is the primary variable that sets the planet's temperature, which, in turn, drives its atmospheric chemistry, its climate, and its potential for habitability. A planet that orbits very close to its star will be subject to an intense and unrelenting bath of stellar radiation. The high temperatures on such a world will mean that its atmosphere is likely to be dominated by refractory and often exotic chemical species. We have found hot Jupiters, for example, with clouds that are made not of water, but of vaporized rock, of silicates and iron. The intense, high-energy radiation from the star can also have a dramatic effect on the atmosphere. The ultraviolet and X-ray flux from a young, active star can heat the upper atmosphere of a close-in planet so much that the gas can escape the planet's gravitational pull, a process called atmospheric escape, or photoevaporation. This process can be so efficient that it can completely strip a planet of its primordial hydrogen and helium-rich atmosphere, leaving behind a bare, rocky core. This is thought to be the origin of a class of exoplanets known as hot Neptunes and super-Earths. They are the resilient survivors of a process of intense stellar sandblasting. A planet that orbits further out from its star in the temperate, habitable zone has a much better chance of retaining a stable, long-lived atmosphere. Here, the temperatures are just right for liquid water to exist on the planet's surface, and the atmospheric chemistry can be much richer and more complex. This is the region where we are most hopeful of finding a world with an atmosphere that is similar to our own, an atmosphere that has been shaped by the interplay of geology, of chemistry, and perhaps of biology. But even in the habitable zone, the distance from the star still matters. A planet on the inner edge of the zone will be more susceptible to a runaway greenhouse effect, like Venus. A planet on the outer edge will be more susceptible to a global glaciation, a snowball state, like the early Mars. The precise long-term stability of a planet's climate depends on a delicate and complex feedback loop between its orbit, its atmosphere, and its geology. And a planet that orbits even further out, in the cold outer reaches of a planetary system, will have a very different kind of atmosphere altogether. Here, the temperatures are so low that the volatile compounds that would be gases on a warmer world, the water, the ammonia, the methane, are frozen solid. The atmospheres of these ice giants, like our own Uranus and Neptune, are composed primarily of the primordial hydrogen and helium that they accreted from the initial protoplanetary disk. The distance of a planet from its star is not just a number, it is a destiny. It is the primary factor that determines the kind of world a planet will become, the kind of atmosphere it will have, and the kind of story that will be written in its skies. And by studying the atmospheres of planets at a wide range of different distances from their stars, we can begin to understand the full and wonderfully diverse range of planetary possibilities that our galaxy has to offer. The habitable zone, or the Goldilocks zone, is a simple but powerful concept that has guided our search for life beyond Earth for decades. It is the region around a star where the temperatures are just right, not too hot, and not too cold for liquid water to exist on the surface of a rocky planet. This is a crucial concept, as liquid water is thought to be the one indispensable ingredient for life as we know it. But the habitable zone is not a fixed, static region of space. Its size and its location depend on the properties of the host star. A small, cool, and dim red dwarf star will have a habitable zone that is much smaller and much closer in than a large, hot, and bright blue giant star. And the habitable zone is not a guarantee of habitability. A planet could be in the right place, but could still be a sterile, lifeless world. Its habitability depends on a host of other factors: its size, its mass, its composition, the presence or absence of a protective magnetic field, its geological activity, and most importantly, the composition and the thickness of its atmosphere. The atmosphere is the key. It is the planet's thermostat, its shield, its chemical laboratory. A planet on the outer edge of the habitable zone could still be warm enough for liquid water if it has a thick greenhouse atmosphere. A planet on the inner edge could be pushed into a runaway greenhouse state if its atmosphere is too rich in water vapor. The concept of the habitable zone is a useful, first-order guide in our search, a way to prioritize the most promising targets for further study. But a true assessment of a planet's habitability requires a much deeper and more holistic understanding of its entire planetary system, and it requires us to be open-minded about the nature of life itself. The habitable zone is defined by the requirements of life as we know it, life that is based on carbon chemistry and that uses liquid water as a solvent. But could there be other forms of life, life as we don't know it, that are based on a different chemistry? A chemistry that could thrive in environments that we would consider to be extreme. Could there be life that uses liquid methane as a solvent, thriving on the cold surface of a world like Saturn's moon Titan? Could there be life that lives not on the surface, but in the deep, subsurface oceans of an icy moon like Europa, an ocean that is kept liquid by the tidal heating from its host planet, far outside the traditional stellar habitable zone? The concept of a galactic habitable zone adds another layer of complexity. It suggests that there may be certain regions of a galaxy that are more conducive to life than others, the very center of a galaxy, with its high density of stars and its intense radiation from a supermassive black hole, might be too dangerous. The very outer edges of a galaxy, with their low abundance of heavy elements, might be too resource-poor. The galactic habitable zone is the sweet spot in between, a cosmic ring of real estate where the conditions for the formation of rocky planets and the emergence of complex life are just right. The search for habitable worlds is a journey that is constantly forcing us to refine, to question, and to expand our own definitions. It is a journey that is not just about finding other Earth-like planets, but is also about understanding the full and wonderfully diverse range of planetary environments that the universe has to offer. And it is a journey that is a powerful reminder that the universe is not just stranger than we imagine, but is likely stranger than we can imagine. The search for life on other worlds is a quest that is fraught with the potential for ambiguity, for false positives, and for the kind of subtle, systemic biases that can lead even the most careful and rigorous scientists astray. The challenge of distinguishing a true biological signal from a purely abiotic, geological or photochemical process that might mimic it is one of the greatest technical and conceptual hurdles in the field of astrobiology. Consider the case of oxygen. It is a powerful and compelling biosignature. But as we have seen, there are known abiotic pathways that can produce it. A wet, rocky planet with a low surface gravity, orbiting a star with a high ultraviolet flux, could, in principle, build up a significant abiotic oxygen atmosphere. Distinguishing this false positive scenario from a true biological one will require a deep and multifaceted understanding of the entire planetary system. We will need to have a precise measurement of the planet's mass and radius, a detailed characterization of its host star's spectrum, and a sensitive search for the presence of other telltale gases, like methane or nitrous oxide. The same ambiguity applies to methane. While it is a powerful biosignature on Earth, it can also be produced by geological processes like serpentinization. The detection of methane on Mars is a beautiful and still unresolved example of this ambiguity. Is it a sign of life or a sign of geology? The answer is still blowing in the thin Martian wind. To navigate this complex and often ambiguous landscape of potential biosignatures, scientists are developing a new, more probabilistic, and more statistically rigorous framework for assessing the evidence for life. This is a framework that is based on Bayesian inference, a method of reasoning that allows us to update our belief in a hypothesis in the light of new evidence. In this framework, a single detection of a potential biosignature is not treated as a definitive proof of life. It is, rather, a piece of evidence that increases our posterior probability that the planet is inhabited. The goal is to build a cumulative case, to gather multiple, independent lines of evidence that all point towards a biological origin. This could include the detection of multiple different biosignature gases in a state of chemical disequilibrium. It could include the detection of a specific and biologically favorable isotopic ratios in one of those gases. It could include the detection of a seasonal variation in the abundance of a gas that is correlated with the planet's seasons. And it could include the absence of any plausible abiotic explanation that can account for all of the observed phenomena simultaneously. The confirmation of life beyond Earth will likely not be a single, dramatic announcement. It will be a slow, careful, and painstaking process of scientific detective work, a process of gradually and collectively building a case that is so strong, so robust, and so well supported by the evidence that it becomes, for all practical purposes, beyond a reasonable doubt. It is a process that will require not just powerful new telescopes and sophisticated new analytical techniques, but also a deep sense of intellectual humility, a constant awareness of our own potential biases, and a willingness to be guided with patience and with rigor by the subtle and often ambiguous. Testimony of the light from other worlds. The technological limitations of our current, and even our near future, instruments are one of the most significant and frustrating barriers in our quest to study the atmospheres of distant exoplanets. The challenges are immense. The light from an exoplanet is incredibly faint, often a billion times dimmer than the light from its host star. And the signal from its atmosphere. The tiny absorption features that are imprinted on the starlight during a transit are even fainter, often just a few parts per million of the total light. To detect and to analyze these incredibly subtle signals requires a telescope with a very large light-gathering mirror, a very stable and sensitive spectrograph, and a very long and often very precious amount of observing time, the Hubble Space Telescope. While a magnificent and versatile instrument was not originally designed for exoplanet atmospheric science. Its mirror is relatively small by modern standards, and its spectrographs are not optimized for the high-precision measurements that are needed for this kind of work. And yet, through the sheer ingenuity and the perseverance of the astronomical community, Hubble has been used to make the first pioneering detections of the atmospheres of a number of hot Jupiter exoplanets. The James Webb Space Telescope is a true game-changer. Its massive 6.5-meter primary mirror and its suite of powerful infrared spectrographs make it the first instrument that is truly optimized for the science of exoplanet atmospheres. It has the sensitivity to detect the atmospheres of smaller, cooler, and more Earth-like planets than was ever possible before. But even Webb has its limitations. It is a single and incredibly oversubscribed facility. The demand for observing time on Webb is so high that only a small fraction of the proposed and scientifically compelling observations can actually be carried out. This means that we will have to be very strategic and very selective in our choice of targets. We will likely be able to get a detailed atmospheric characterization for only a handful of the most promising and most nearby potentially habitable exoplanets in the coming years. Another major limitation is the noise from the host star itself. A star is not a perfect, stable, and uniform source of light. It has star spots. It has flares. It has other forms of magnetic activity, all of which can cause its brightness to vary in a way that can mimic, or can obscure, the tiny signal from a transiting planet's atmosphere. The development of sophisticated data analysis techniques to model and to remove this stellar noise is one of the most critical and challenging areas of ongoing research in the field. And finally, there are the limitations of our own theoretical models. To interpret the spectrum of an exoplanet's atmosphere, to translate the pattern of absorption lines into a statement about the presence and the abundance of different gases. We need to have a detailed and accurate model of how light interacts with matter under the specific and often extreme temperature and pressure conditions of that atmosphere. These models are based on a vast amount of laboratory data and a deep theoretical understanding of atomic and molecular physics. But there are still many uncertainties, particularly for the more exotic molecules and for the extreme conditions that may exist on some of these alien worlds. The study of exoplanet atmospheres is a field that is constantly pushing at the very edge of what is technologically and scientifically possible. It is a field that requires a constant and often creative dialogue between the observers, who are trying to squeeze every last precious photon of information from their data, and the theorists, who are trying to build the models that can make sense of it all. And it is a field that is a powerful testament to the human spirit of exploration, to our relentless and beautiful desire to see, to know, and to understand, even in the face of the most immense and the most daunting of all cosmic challenges. The future of exoplanet atmospheric science is an incredibly bright and exciting one. We are standing on the threshold of a new era of discovery, an era that will be defined by a new generation of incredibly powerful and often highly specialized telescopes, both on the ground and in space. The James Webb Space Telescope is the vanguard of this new era, but it is just the beginning. The European Space Agency's Ariel mission, scheduled for launch in the late 2020s, will be the first space telescope that is entirely and exclusively dedicated to the science of exoplanet atmospheres. It will perform a large-scale survey, studying the atmospheres of about 1,000 different transiting exoplanets, from the hot gas giants to the temperate, rocky worlds. By studying such a large and diverse sample, Ariel will allow us to perform a kind of comparative exoplanetology on a grand scale. We will be able to search for the statistical trends and the correlations between a planet's atmospheric composition and its other properties, like its mass, its size, and the type of star it orbits. This will be a crucial step in moving from the detailed study of a few individual worlds to a more general and more powerful understanding of the processes that shape the atmospheres of planets across the galaxy. On the ground, a new generation of extremely large telescopes, with primary mirrors that are 20 to 40 meters in diameter, are now under construction. These giant terrestrial observatories, with their immense light-gathering power and their sophisticated adaptive optic systems, will be able to study exoplanet atmospheres with a level of detail and precision that is simply not possible with our current ground-based facilities. They will be able to use the technique of high-resolution spectroscopy to resolve the individual spectral lines of molecules in a planet's atmosphere, allowing for a much more definitive and unambiguous detection of different gases. And they will be the first instruments that have a real and exciting chance of directly imaging a true Earth-like planet orbiting a nearby star, and of analyzing the faint, reflected light from its atmosphere to search for the biosignatures of oxygen and water, looking even further into the future. NASA is now in the early stages of designing a new, large, space-based flagship observatory for the 2040s. A telescope that is currently being referred to as the Habitable Worlds Observatory. This would be a true, direct successor to Hubble and Webb, a telescope with a large 6 to 15 meter mirror that would be specifically designed and optimized for the ultimate goal of exoplanet science, the direct imaging and the spectroscopic characterization of dozens of potentially habitable, Earth-like planets in the habitable zones of the nearest Sun-like stars. This is a mission of immense and multi-generational ambition, but it is a mission that holds the promise of a discovery that would forever change the course of human history. It is a mission that could, one day, provide us with a definitive and beautiful answer to the ancient and enduring question of whether we are alone in the universe. The future of our search for other worlds is a future of incredible promise, a future where we will move from the first tentative detections to a detailed and deeply profound understanding of the rich and diverse tapestry of planets that fills our galaxy. And it is a future that is a testament to our own, unique, and perhaps most defining human characteristic, our endless and unquenchable curiosity. The presence of clouds in the atmosphere of an exoplanet is a double-edged sword for the astronomers who are trying to study these distant worlds. On the one hand, clouds are a powerful and often essential ingredient for planetary habitability. They are a sign of a dynamic, and often water-rich, atmosphere. They play a crucial role in a planet's climate, reflecting a portion of the incoming starlight back into space and thus cooling the planet, while also trapping the outgoing thermal radiation and thus warming it. They are the key players in a planet's hydrological cycle, transporting water from the oceans to the continents. And on Earth, they are one of the most beautiful and dynamic features of our own living world. The detection of water clouds in the atmosphere of a temperate, rocky exoplanet would be an incredibly exciting discovery, a powerful and deeply suggestive piece of evidence that the planet might harbor a stable, liquid water ocean on its surface. But on the other hand, clouds are the bane of the exoplanet spectroscopist's existence. A thick, high-altitude cloud deck can act like a shroud, completely obscuring our view of the lower and often more interesting layers of the atmosphere. When we try to do transmission spectroscopy on a cloudy planet, the starlight is simply blocked by the opaque clouds, and we are left with a flat, featureless, and deeply uninformative spectrum. This has been a major source of frustration for astronomers using the Hubble Space Telescope, as a significant fraction of the potentially habitable super-Earth and mini-Neptune planets that have been observed have turned out to have these high-altitude and spectroscopically frustrating clouds or hazes. The challenge of seeing through the clouds is one of the primary and technical drivers for the design of the next generation of exoplanet-characterizing telescopes. The James Webb Space Telescope, with its sensitivity to longer infrared wavelengths, has a better chance of peering through these clouds than Hubble did, as infrared light is less susceptible to being scattered by small cloud particles, and future direct imaging missions will be able to study the reflected light from the tops of the clouds themselves. By observing the subtle, periodic changes in the planet's brightness and color as it rotates, we can begin to map the distribution of the clouds across the planet's surface. We can look for the signs of large, stable weather patterns, like the Great Red Spot on Jupiter. And we can even try to distinguish between different types of clouds, the bright, white, and highly reflective water clouds that are a potential sign of a habitable world, and the darker, more absorbing silicate or soot clouds that are a sign of a much more exotic and likely inhospitable environment. The study of clouds on exoplanets is a new and exciting frontier in the field of comparative planetology. It is a field that is forcing us to think in new and creative ways about the complex, and often beautiful, interplay between a planet's atmosphere, its climate, and its potential for life. And it is a field that is a powerful reminder that the universe is not just a collection of simple, static, and easily characterizable worlds, but is a rich and diverse zoo of complex, dynamic, and often beautifully cloudy planetary systems. The detection of ozone in the atmosphere of an exoplanet would be another powerful and deeply significant piece in the complex puzzle of the search for life. Ozone, a molecule made of 3 oxygen atoms, is a substance that is intimately and inextricably linked to the presence of free molecular oxygen in a planet's atmosphere. It is formed in the upper atmosphere when high-energy, ultraviolet radiation from the host star splits a normal 2-atom oxygen molecule apart, and the resulting highly reactive single oxygen atoms then combine with other unsplit oxygen molecules. This process creates a protective ozone layer, a shield that absorbs the most harmful, high-energy ultraviolet radiation from the star, preventing it from reaching the planet's surface. On Earth, the ozone layer is absolutely essential for the existence of complex life on land. Without it, the sun's ultraviolet radiation would be so intense that it would sterilize the surface, destroying DNA and other crucial biological molecules. The evolution of the ozone layer, which occurred in the wake of the Great Oxidation Event, was a critical and perhaps necessary step in the journey of life from the protective depths of the oceans to the more challenging, but also more energy-rich, environment of the continents. So, when we look for ozone in the atmosphere of an exoplanet, we are looking for 2 crucial things at once. First, we are looking for an indirect, but very powerful, confirmation of the presence of a significant amount of free oxygen. Ozone has a very strong and very characteristic absorption feature in the ultraviolet part of the spectrum, and in some cases it may be even easier to detect than the oxygen itself. A definitive detection of ozone would be a strong and deeply exciting piece of evidence for an oxygen-rich atmosphere. Second, we are looking for a sign that the planet has a built-in protective shield, a shield that could make its surface environment much more hospitable to the kind of complex, and perhaps even intelligent, life that we are ultimately searching for. The detection of ozone is one of the primary scientific goals of the next generation of large, space-based telescopes that are now being designed. A telescope with a sensitive, ultraviolet spectrograph could, in principle, detect the ozone absorption feature in the transmission spectrum of a nearby, transiting, Earth-like planet. This would be a discovery of immense and truly historic proportions. It would not, in itself, be a definitive proof of life, but it would be a powerful and deeply suggestive piece of a larger cumulative case. It would be a sign that we have, perhaps, finally found a world that is not just habitable in a theoretical sense, but is a world that has been fundamentally and beautifully shaped by the presence of a living, breathing, and planet-altering biosphere. The challenge of detecting a definitive and unambiguous biosignature from a distant exoplanet is one of the most difficult and most profound in all of science. It is a challenge that is not just about building bigger telescopes and more sensitive instruments. It is also a deep, conceptual challenge, a challenge that forces us to confront the limits of our own knowledge, the potential for our own biases, and the very definition of life itself. The primary technical challenge is one of signal to noise. The signal from an exoplanet's atmosphere is incredibly faint, and it is buried in the overwhelming glare of its host star. To extract this tiny signal, we must have an almost perfect understanding of the star itself, of its own intrinsic variability, of its spots, its flares, its pulsations. We must be able to model and to remove this stellar noise with incredible precision, to be sure that the faint absorption feature we are seeing is truly from the planet, and not just an uncorrected artifact of the star's own complex behavior. The problem of false positives is another major and deeply concerning challenge. The universe is a vast and a complex place, and it has a rich and a creative chemistry. There may be abiotic, geological, or photochemical pathways that can produce the very same potential biosignature gases that we are searching for. We must be the ultimate cosmic detectives, carefully and rigorously ruling out all possible, non-biological explanations for an observed signal before we can even begin to entertain the possibility of a biological origin. This will require a deep and deeply interdisciplinary approach, a collaboration between astronomers, planetary scientists, geologists, chemists, and biologists. The challenge is also a profoundly philosophical one. Our entire search for biosignatures is, at present, based on a single and perhaps unrepresentative example. Life on Earth. We are searching for the signs of life as we know it, life that is based on carbon chemistry, that uses liquid water as a solvent, and that produces a specific and detectable set of atmospheric byproducts. But what if life on other worlds is fundamentally different? What if it is based on a different, and to us, an exotic biochemistry? What kind of biosignatures would such a life as we don't know it produce? This is the challenge of agnostic biosignatures, the search for the more general and less Earth-centric signs of life. This could be the search for a planetary scale, thermodynamic disequilibrium, for an atmosphere that is so far from a state of chemical equilibrium that it requires a constant and powerful input of energy to maintain, an input that could be the signature of a living, planetary-scale metabolism, or it could be the search for extreme, and otherwise unexplainable, complexity in the molecular composition of an atmosphere. The detection of a potential biosignature will not be the end of the story. It will be the beginning of a long and often difficult process of scientific debate and verification. It will be a process that will require a deep sense of intellectual humility, a constant willingness to question our own assumptions, and a profound respect for the high and historic stakes of the claim being made. The search for life beyond Earth is not a race. It is a careful and deeply collaborative human endeavor, an endeavor that is worthy of our best and most rigorous scientific and philosophical efforts. The use of sophisticated and increasingly complex computer models is an absolutely essential part of our modern scientific quest to understand the atmospheres of distant exoplanets. The data we receive from our telescopes is not a direct, unambiguous picture of an alien world. It is a sparse, noisy, and often degenerate set of measurements, a collection of photons that has been filtered through a complex and largely unknown physical system to translate this raw data into a meaningful scientific understanding to infer the temperature, the pressure, the composition, and the potential habitability of an exoplanet's atmosphere. We must rely on the power of our theoretical and computational models. The process begins with the development of a forward model. This is a computer simulation that takes a set of assumed physical properties for a planet and its atmosphere, its size, its mass, its temperature, the abundance of different gases, and it predicts the observable signal that we would expect to see with our telescope. For example, the transmission spectrum during a transit. This forward model is a complex and deeply interdisciplinary piece of software. It must include a detailed quantum mechanical model of how light interacts with all the different atoms and molecules that might be present in the atmosphere. It must include a model of the atmosphere's temperature and pressure structure, which is often derived from a more complex general circulation model that simulates the planet's global climate. And it must include a model of the host star, of its own intrinsic spectrum, of its spots, its flares, its limb darkening. Once we have this forward model, we can then perform the process of retrieval or inversion. This is the process of comparing the predictions of our model with the actual observational data, and of adjusting the parameters of the model until we find the best possible fit. This is often a complex and computationally intensive statistical problem, one that involves exploring a vast, multidimensional parameter space to find the combination of atmospheric properties that is most consistent with the data. This is where modern machine learning techniques are becoming increasingly powerful. An AI system can be trained on a vast, pre-computed library of millions of different simulated atmospheric spectra. It can learn the complex and often nonlinear relationship between the atmospheric properties and the resulting spectrum. It can then be used to rapidly and efficiently analyze a new, observed spectrum, providing a fast and often very accurate estimate of the planet's atmospheric composition. But our models are only as good as the assumptions that go into them. And in the field of exoplanet science, where we are often dealing with worlds that are very different from the ones in our own solar system, we must be constantly vigilant about the limitations of our own theoretical frameworks. We must be willing to question our assumptions, to explore a wide range of different possible models, and to be honest about the uncertainties and the degeneracies that are inherent in our analysis. The use of computer models in exoplanet science is a beautiful and often frustrating dialogue between theory and observation. The observations provide the data that can test and constrain our models, and the models provide the theoretical framework that allows us to make sense of the data, to translate the wiggles in a spectrum into a story about a distant and alien world. It is in this iterative and deeply collaborative dance between the real and the simulated, between the observed and the imagined, that our true and ever-deepening understanding of the cosmos is born. The surface of an exoplanet is a hidden and largely inaccessible realm. For the most part, our observations are limited to the thin gaseous envelope of its atmosphere. And yet, The nature of the surface, whether it is a solid, rocky crust, a deep global ocean, or the fuzzy, ill-defined top of a gas giant, is a critical and often dominant factor in shaping the properties of the atmosphere that we can see. The surface and the atmosphere are not two separate, independent systems. They are a single, deeply interconnected, and co-evolving system. The surface of a rocky planet, for example, is a major source and sink for many of the most important atmospheric gases. Volcanic eruptions can release vast quantities of carbon dioxide, water vapor, and sulfur compounds into the atmosphere, fundamentally shaping its composition and its climate over geological timescales. The process of rock weathering, on the other hand, can remove carbon dioxide from the atmosphere, acting as a long-term planetary thermostat. The interaction between a planet's oceans and its atmosphere is another crucial and deeply dynamic feedback loop. The oceans are a vast reservoir of water which can evaporate to form clouds and to drive a global hydrological cycle. They are also a major sink for atmospheric carbon dioxide, which can dissolve in the seawater and be sequestered in the deep ocean, helping to regulate the planet's climate. The nature of the surface also determines the planet's albedo, its overall reflectivity. A planet with bright, icy poles and reflective, white clouds will reflect more of the incoming starlight back into space and will be cooler than a planet with dark, rocky continents and deep, blue, absorbing oceans. This albedo feedback is a critical component of a planet's climate system. A small initial cooling can lead to the growth of the ice caps, which increases the planet's albedo, which leads to further cooling, in a potential runaway snowball feedback loop. To understand the atmosphere of an exoplanet, then we must also, in some way, try to understand its surface. This is an incredibly challenging task, but there are a few subtle clues that we can look for. By observing the subtle, periodic variations in the reflected light from a directly imaged planet as it rotates, we can begin to create a crude, longitudinal map of its surface features. We can look for the characteristic, spectral signature of the red edge of vegetation, a sharp increase in the reflectivity of plants in the near-infrared that is a potential and powerful surface biosignature, and we can use our sophisticated climate models to try and infer the likely surface conditions that are most consistent with the observed atmospheric properties. The study of the surface-atmosphere interaction on exoplanets is a new and deeply challenging frontier, but it is an essential one. It is the key to moving from a simple, one-dimensional laundry list of atmospheric gases to a more holistic, more dynamic, and more deeply satisfying understanding of these distant worlds as true, integrated, and potentially living planetary systems. A planet's magnetic field is an invisible, but absolutely essential shield that can play a decisive role in its long-term habitability. It is the silent, unsung hero in the story of a planet's ability to hold on to its precious and often life-sustaining atmosphere. The source of a planet's magnetic field is a dynamo in its deep interior, a process that requires a rotating, convecting, and electrically conducting fluid core. On Earth, this is the molten iron-nickel outer core. The magnetic field that is generated by this dynamo extends far out into space, creating a protective magnetic bubble around the planet, the magnetosphere. This magnetosphere acts as a shield, deflecting the constant stream of high energy, charged particles that are flowing out from the star, the stellar wind. Without this protective shield, the stellar wind would be able to directly impact the upper atmosphere of the planet, slowly but inexorably, stripping it away into space. This is thought to be a major part of the story of what happened to Mars. Mars, a smaller planet than the Earth, cooled down more quickly in its interior. Its dynamo is thought to have shut down about 4 billion years ago. And without the protection of a global magnetic field, the solar wind has, over the subsequent geological eons, stripped away the vast majority of what was once a much thicker and perhaps even life-supporting Martian atmosphere. A strong global magnetic field, then, is likely to be a crucial and perhaps even a necessary condition for a planet to maintain a stable, long-lived atmosphere, and therefore for it to be a viable, long-term abode for life. The detection of magnetic fields on exoplanets is an incredibly challenging, but deeply important, new frontier in astronomical research. We cannot, of course, send a magnetometer to these distant worlds, but we can search for the indirect radio signature of their magnetospheres. The interaction between the charged particles of the stellar wind and a planet's magnetic field can generate powerful low-frequency radio emissions, similar to the auroral radio emissions that are generated in the Earth's own polar regions. A number of large, ground-based radio telescopes are now being used to conduct the first sensitive searches for these exoplanetary auroral radio emissions. A definitive detection of such a signal would be a groundbreaking discovery. It would be the first direct confirmation of the existence of a magnetic field on an exoplanet. And it would provide us with a powerful, new tool for assessing the potential habitability of these distant worlds. It would allow us to identify the planets that are not just in the right place, but are also, in a very real and a very important sense, well protected. The geological activity of a planet, the slow and often violent churning of its interior, is another crucial and often overlooked ingredient in the complex recipe for long-term habitability. A geologically dead planet is likely to be a biologically dead planet. Volcanic activity, in particular, plays a vital role in shaping and in maintaining a planet's atmosphere. The outgassing from volcanoes is a major source of many of the most important atmospheric gases, including water vapor, carbon dioxide, and nitrogen. This process can help to create a planet's initial secondary atmosphere, and it can also help to replenish an atmosphere that is being slowly lost to space. Volcanism is also a key player in the long-term planetary climate regulation of the carbonate-silicate cycle. This is a beautiful and deeply important feedback loop that acts as a global thermostat, keeping the Earth's climate stable over geological timescales. The process, as we have seen, involves the removal of carbon dioxide from the atmosphere by rock weathering, its sequestration on the ocean floor in the form of carbonate rocks, and its eventual return to the atmosphere through volcanic activity. A planet without active plate tectonics and volcanism would not have this crucial climate-stabilizing mechanism. It would be much more susceptible to either a runaway greenhouse effect or a global glaciation. A geologically active interior is also the source of a planet's magnetic field, which, as we have seen, is essential for protecting its atmosphere. And the same internal heat that drives volcanism can also create localized hydrothermal environments, like the deep-sea vents on the Earth's ocean floor. These environments, with their rich chemical gradients and their abundant, non-solar energy sources, are thought by many to be one of the most plausible locations for the origin of life itself. A geologically active planet, then, is a living, breathing planet. A planet that is constantly renewing its surface, recycling its elements, and maintaining the dynamic, and often life-sustaining, disequilibrium that is the hallmark of a habitable world. The search for the signs of geological activity on exoplanets is an incredibly challenging, but deeply important, new frontier. We can search for the telltale spectroscopic signature of volcanic gases, like sulfur dioxide, in a planet's atmosphere. We can use the technique of phase curve analysis to look for the thermal signature of active volcanoes on a planet's surface. And we can use our theoretical models to try and infer the likely internal state of a planet based on its mass, its size, and its age. The discovery of a geologically active, living Earth-like planet orbiting another star would be a discovery of immense and truly profound scientific significance. It would be a powerful sign that we have found a world that has not just the raw ingredients for life, but also the long-term, stable, and dynamic environmental conditions that are likely necessary for life to arise, to survive, and to flourish. The type of star that an exoplanet orbits is another, crucial and often dominant, factor in determining its potential for habitability. Stars are not all created equal. They come in a wide and beautiful variety of sizes, of temperatures, of colors, and of ages, and each of these different types of stars creates a very different and often very challenging environment for its orbiting planets. The vast majority of stars in our galaxy, about 75% of them, are red dwarfs. These are stars that are much smaller, much cooler, and much dimmer than our own. Sun-like stars. Because they are so dim, their habitable zones are much smaller and much closer in. This has a number of profound and often problematic implications for the habitability of their planets. A planet in the habitable zone of a red dwarf would be tidally locked, with one side permanently facing the star and the other side permanently facing away. This would create a world of extreme and potentially life-prohibiting temperature contrasts between a scorching, eternal day side and a frozen, eternal night side. The planet's only hope for a stable climate would be a thick atmosphere that could efficiently transport heat from the day side to the night side. Young red dwarfs are also notoriously active and volatile. They can unleash powerful superflares that are thousands of times more energetic than the flares from our own sun. A planet orbiting in the close-in, habitable zone of such a star would be repeatedly bathed in a lethal bath of high-energy radiation and charged particles, a process that could strip away its atmosphere and sterilize its surface. This has led many to conclude that, despite their sheer numerical abundance, red dwarf systems may not be the most promising places to search for life. On the other end of the stellar spectrum are the large, hot, and bright A-type and B-type stars. These stellar behemoths have a habitable zone that is much wider and much further out than that of a sun-like star, but they also have a very short and very violent lifespan. They burn through their nuclear fuel in just a few 100 million years, a time scale that may not be long enough for complex life to evolve. And their intense, high-energy ultraviolet radiation would create a very harsh and challenging environment for any life that did manage to get a foothold. It seems, then, that the sweet spot for habitability may be around stars that are similar to our own sun, the G-type and the K-type stars. These are stars that are stable, that are long-lived, and that provide a relatively benign and constant source of energy for their orbiting planets. They are, in a sense, the Goldilocks stars. Not too hot, not too cold, not too violent, not too short-lived. This does not mean that life is impossible around other types of stars. The universe is a vast and a creative place, and life may have found a way to thrive in environments that we would consider to be extreme. But it does suggest that, as we begin our first tentative searches for the signs of life on other worlds, the planets orbiting the quiet, stable, and sun-like stars in our own local galactic neighborhood may be the most promising and the most logical places to start looking. The search for life on super-Earths, a class of exoplanets that are more massive than the Earth but less massive than Neptune, is one of the most exciting and rapidly developing frontiers in astrobiology. These are worlds that have no direct analog in our own solar system, and they appear to be one of the most common types of planets in the galaxy. Their potential for habitability is a subject of intense and often fascinating scientific debate. On the one hand, a super-Earth could be a super-habitable world, a planet that is even better suited for life than our own. A planet that is slightly more massive than the Earth could have a stronger gravitational pull, which would allow it to hold on to a thicker and more protective atmosphere. It could also have a more vigorous and more long-lived plate tectonic activity, which would be beneficial for long-term climate stability and for the cycling of crucial life-sustaining nutrients. A super-Earth with a higher fraction of water could be a true water world, a planet with a deep global ocean that could be a vast and incredibly stable habitat for life. On the other hand, there are a number of potential and serious challenges to the habitability of super-Earths. A planet that is too massive might be able to hold on to a thick primordial atmosphere of hydrogen and helium, which would create a crushing surface pressure and a runaway greenhouse effect, making it more like a mini Neptune than a scaled-up Earth. A very deep global ocean could also be a problem. The immense pressure at the bottom of such an ocean could create a layer of exotic, high-pressure ice, which would effectively seal off the ocean from the geological activity of the rocky seafloor, cutting off a crucial source of nutrients. The key to distinguishing between these different possible scenarios lies in the study of their atmospheres. By measuring the composition of a super-Earth's atmosphere, we can begin to infer the nature of its surface and its potential for habitability. The detection of a significant amount of water vapor, for example, would be a strong indication of a water-rich world. The detection of a secondary, nitrogen-rich atmosphere, as opposed to a primordial, hydrogen-rich one, would be a good sign that the planet is a true, rocky super-Earth, and not a mini Neptune. And, of course, the ultimate goal is to search for the telltale biosignature gases, like oxygen and methane. That could be the first, tantalizing hint of a living, breathing, and super-habitable world. The study of super-Earths is a journey into a new and uncharted territory of planetary science. It is a journey that is forcing us to expand our own, often Earth-centric, ideas of what a habitable world might look like. And it is a journey that is a powerful reminder that the universe is a place of incredible and often surprising diversity. A place where the most common type of planet in the galaxy may be a type of world that we have never seen before. A world that could be, in every sense of the word, better than our own. The question of whether life could exist on or in the atmospheres of gas giant planets, like our own Jupiter and Saturn, is one of the most speculative and most romantic in all of astrobiology. It is an idea that was famously and beautifully explored by the astronomers Carl Sagan and E. Salpeter in the 1970s. They envisioned a complex and self-contained aerial ecosystem in the thick, turbulent atmosphere of a Jupiter-like planet. They imagined three different kinds of organisms: the sinkers, small, microscopic creatures that were constantly falling towards the hot, deep interior of the planet; the floaters, vast, hydrogen balloon-like organisms, kilometers in diameter, that could stay aloft in the upper atmosphere by actively managing their own buoyancy; and the hunters, fast, agile, jet-propelled predators that would fight on the slow-moving floaters. This was a beautiful and scientifically plausible piece of speculative biology. It was based on the recognition that, while the surface of a gas giant, if it even has one, is a place of crushing pressures and extreme temperatures, there is a layer in its atmosphere, a temperate, habitable zone, where the temperatures and the pressures are just right for liquid water droplets to exist. And where there is liquid water, there is, at least in principle, the possibility of life. The challenge, of course, is that this habitable zone is not a stable place. The powerful vertical winds and the turbulent convection of a gas giant's atmosphere would be constantly trying to pull any hypothetical aerial life forms down into the hot, deep interior where they would be destroyed, or to loft them up into the cold, upper atmosphere where they would freeze. Any life form that hoped to survive in this environment would have to evolve a powerful and efficient means of actively maintaining its own altitude. The floaters of Sagan and Salpeter are one hypothetical solution to this problem. But even if life could solve this fundamental dynamical challenge, it would still face a number of other serious hurdles. The energy sources in this atmospheric and habitable zone are limited, the sunlight is weak, and it is often blocked by the thick overlying cloud decks. The chemical energy gradients may not be as strong as they are in a more geologically active, rocky world. And the nutrients, the heavy elements that are necessary for the chemistry of life, are present in only very small and trace quantities in the overwhelmingly hydrogen and helium-rich atmosphere of a gas giant. Despite these challenges, the possibility of life in the clouds of gas giants cannot be entirely ruled out. The universe is a vast and a creative place, and life has shown itself to be remarkably tenacious and adaptable here on Earth. The search for the signs of such a life is, of course, an incredibly difficult one. We can search for the telltale biosignature gases, the chemical disequilibria, in the atmospheres of these planets. The recent and highly controversial claim of the detection of phosphine in the atmosphere of Venus is a beautiful and deeply intriguing example of this kind of search. Phosphine on Earth is a gas that is almost exclusively associated with anaerobic microbial life, finding it in the temperate and potentially habitable cloud decks of Venus was a tantalizing, though still highly uncertain, hint that a form of aerial, microbial life might be thriving in the most unlikely of places. The search for life in the atmospheres of gas giants is a journey to the very edge of our scientific and our imaginative capabilities. It is a journey that forces us to think in new and creative ways about the very definition of a habitable environment, and about the wonderfully diverse and often surprising forms that life might take in a universe that is full of possibilities. The concept of chemical disequilibrium is one of the most powerful and most general principles in our search for life beyond Earth. It is a concept that is rooted in the fundamental laws of thermodynamics, and it provides us with a potential agnostic biosignature, a sign of life that is not tied to the specific and perhaps parochial details of our own terrestrial biochemistry. A living organism is, in its very essence, a system that is far from a state of chemical equilibrium. It is a highly ordered and deeply improbable arrangement of matter that is constantly taking in energy and matter from its environment, using it to maintain its own internal order and to create new, ordered structures, and then expelling the waste products back into the environment. A living being is a dissipative structure, a localized and temporary whirlpool of low entropy in the midst of the universe's relentless and overall journey towards a state of greater entropy. And this process of life, this constant metabolic churning, can have a powerful and detectable impact on the chemistry of its entire planetary scale environment. A planet with a living and globally significant biosphere will be a planet whose atmosphere is in a state of profound and persistent chemical disequilibrium. We have already seen the most famous example of this, the coexistence of oxygen and methane in the Earth's atmosphere. This is a chemical mixture that is about as stable as a mixture of gasoline and lit matches. It should not exist. The only reason it does is that life is constantly and powerfully pumping both of these reactive gases into the atmosphere, maintaining a state that is billions of times out of equilibrium. The search for this kind of planetary scale, chemical disequilibrium, is one of the primary scientific goals of the James Webb Space Telescope and of the future exoplanet characterizing missions that are now being designed. By taking a detailed chemical inventory of an exoplanet's atmosphere, by measuring the abundances of all the major and many of the minor gaseous species, we can begin to ask a very simple but very profound question: is this atmospheric mixture something that can be explained by the known and predictable processes of geology and photochemistry alone, or does it require something more? Does it require the introduction of a new and powerful and planet-altering force? Does it require the presence of life? This is a challenging and deeply interdisciplinary task. It requires us to have a detailed and very accurate model of all the possible abiotic processes that can shape a planet's atmosphere. We need to understand the outgassing from its volcanoes, the chemical reactions that are driven by the light from its star, the exchange of gases between its atmosphere and its oceans. It is only when we have a full and comprehensive null hypothesis, a complete model of what a dead planet should look like, that we can begin to search for the subtle and statistically significant deviations from this baseline that could be the first telltale whisper of an alien biology. The search for chemical disequilibrium is a search for a planet that is, in a very real and a very thermodynamic sense, alive. It is a search for a world that is not just a passive and slowly decaying chemical system, but is an active, dynamic, and creative one. A world that has been fundamentally and beautifully transformed by the strange and wonderful and deeply disequilibrating miracle of life. The long-term habitability of a planet, its ability to maintain the stable and life-friendly conditions on its surface for the billions of years that are likely necessary for the evolution of complex and perhaps even intelligent life, is a story that is largely written in the fate of its atmosphere. An atmosphere is a fragile and a precious thing, and a planet's ability to hold onto it over geological timescales is a key and often overlooked aspect of its potential to be a true and enduring cradle of life. The primary threat to a planet's atmosphere is the process of atmospheric escape, the slow and often relentless leakage of its atmospheric gases into the cold, empty vacuum of space. There are a number of different physical mechanisms that can drive this escape. For a small, low-mass planet, the most important of these is Jeans escape, a process where the individual atoms and molecules in the hot upper atmosphere can be moving so fast that their thermal velocity exceeds the planet's escape velocity, the speed that is needed to break free from its gravitational pull. This process is particularly efficient for the light, and therefore fast-moving, gases like hydrogen and helium. This is why the small, rocky, terrestrial planets in our own solar system have lost their primordial, hydrogen and helium-rich atmospheres, while the massive gas giant planets have been able to hold on to theirs. Another, and often more dramatic, mechanism is the stripping of an atmosphere by the stellar wind, the constant stream of high-energy, charged particles that are flowing out from a star. A planet with a strong global magnetic field, like the Earth, is well protected from this stellar wind. Its magnetosphere acts as a shield, deflecting the charged particles around the planet, but a planet without a magnetic field, like Mars, is much more vulnerable. The solar wind can directly impact its upper atmosphere, knocking the atmospheric atoms and molecules out into space in a process that is akin to a slow cosmic-scale sandblasting. This is thought to be the primary reason that Mars has lost the vast majority of its once much thicker atmosphere over the course of its history, and the intense, high-energy radiation from a star, particularly its ultraviolet and X-ray emission, can also drive a powerful atmospheric escape, a process called photoevaporation. This is a particularly important process for the close-in exoplanets that we are now discovering in large numbers. A small, rocky planet that is orbiting very close to its star can have its entire atmosphere, and even a portion of its rocky surface, literally boiled away by the intense stellar radiation. The study of atmospheric escape is a crucial and deeply important part of our assessment of the habitability of exoplanets. It is a field that requires a deep and deeply interdisciplinary understanding of the complex interplay between a planet's mass, its size, its composition, its magnetic field, and the properties of its host star. It is a field that is forcing us to think not just about the habitable zone in a static sense, but about the long-term, dynamic, and often precarious. Evolution of a planet's habitability over the course of its entire multi-billion-year life. And it is a field that is a powerful and deeply humbling reminder of the many, and often fortunate, circumstances that have allowed our own beautiful and life-bearing planet to hold on to its precious and life-sustaining atmospheric breath for over 4 billion years. The thousands of exoplanets that we have now discovered are not just a collection of abstract data points. They are a zoo of new, and often wonderfully strange, worlds, a testament to the incredible and often surprising diversity of the planetary formation process. We have found hot Jupiters, gas giant planets that orbit their stars in a matter of days, their atmospheres heated to thousands of degrees. We have found super-Earths and mini-Neptunes, planets with sizes and masses that are intermediate between the rocky and the gaseous planets of our own solar system. We have found planets that orbit 2 stars. Tatooine worlds with 2 suns in their sky. We have found rogue planets that have been ejected from their home systems and now wander the cold, dark emptiness of interstellar space. And, most excitingly, we have begun to find a growing number of small, rocky, and potentially habitable worlds orbiting in the temperate Goldilocks zones of their stars. One of the most famous and most promising of these is the Proxima Centauri B system. Proxima Centauri is our nearest stellar neighbor, a small, cool red dwarf star that is just 4.2 light-years away. And in 2016, astronomers discovered a small, at least 1.3 times the mass of the Earth, planet orbiting it in a tight 11-day orbit. This planet, Proxima b, lies squarely in the middle of its star's habitable zone. This is a discovery of immense and truly historic significance. For the first time, we have found a potentially habitable, Earth-sized world orbiting our very nearest stellar neighbor. This makes it a prime target for future follow-up observations, and even in the far future, for the first robotic interstellar probes. The TRAPPIST-1 system is another, equally exciting and deeply intriguing discovery. This is a system of at least 7, roughly Earth-sized, rocky planets, all orbiting a tiny, ultra-cool red dwarf star that is about 40 light-years away. And what is truly remarkable is that at least 3, and possibly as many as 4, of these planets lie within the star's habitable zone. This is a compact and wonderfully rich natural laboratory for the study of the formation and the evolution of potentially habitable terrestrial planets. The James Webb Space Telescope is now in the process of studying the atmospheres of these TRAPPIST-1 planets, searching for the telltale chemical fingerprints of water, of carbon dioxide, and perhaps even of life itself. And we are finding a growing number of other equally compelling candidates. The planet Kepler-186f was the first roughly Earth-sized planet to be discovered in the habitable zone of another star. The planet K2-18b is a super-Earth with a significant atmosphere that has been shown to contain water vapor. The list is growing longer with every new survey, with every new analysis. Each of these new worlds is a new and unique data point in our quest to understand the prevalence of habitable and perhaps inhabited worlds in our galaxy. And each of them is a new and powerful source of inspiration, a new distant shore in the vast cosmic ocean that is inviting us to come and to explore. The age of exoplanets is an age of profound and deeply human discovery, an age where we are, for the first time, beginning to see our own small and very special world not as a unique and isolated miracle, but as one of a vast and wonderfully diverse family of planets, a family that is spread throughout the beautiful and perhaps the wonderfully alive tapestry of the cosmos. The transit method, with its simple but powerful logic of watching for the faint, periodic dip in a star's light, has been the undisputed king of exoplanet detection for the past 2 decades. It is a technique that is responsible for the vast majority of the thousands of exoplanets that we have now discovered. But the true, and perhaps most profound, power of the transit method lies not just in its ability to find new worlds, but in its unique ability to provide a window into their atmospheres. As we have seen, when a planet passes in front of its star, a tiny fraction of the starlight is filtered through the thin, gaseous annulus of its atmosphere. By carefully analyzing the spectrum of this filtered light, a technique called transmission spectroscopy, we can search for the chemical fingerprints of the gases that are present in that atmosphere. This is a technique of almost unimaginable subtlety and precision. The atmospheric signal is typically only a few, tens or hundreds of parts per million of the total stellar light. To detect this tiny signal requires a telescope with an incredible stability, a very high sensitivity, and the ability to stare at a single star for many, many hours, patiently accumulating the faint atmospheric photons. But the rewards are immense. The transmission spectrum of an exoplanet's atmosphere is a rich and wonderfully informative data set. It can tell us about the presence of a wide range of different molecules, from the simple, like water and carbon dioxide, to the more complex and potentially life-indicating, like methane and ozone. It can tell us about the temperature and the pressure of the atmosphere. And it can tell us about the presence of clouds or hazes, which can have a profound impact on a planet's climate and its potential for habitability. The James Webb Space Telescope, with its massive infrared-optimized mirror and its suite of powerful and highly specialized spectrographs, is a machine that has been built, in large part, to master the art of transmission spectroscopy. It is a telescope that is allowing us to take the first, detailed, and truly groundbreaking chemical inventory of the atmospheres of a diverse range of exoplanets, from the giant, hot Jupiters to the small, temperate, and potentially habitable super-Earths. The transit method is a powerful but also a very biased technique. It can only find the planets whose orbits happen to be perfectly aligned with our line of sight, a small fraction of the total planetary population. And it is most sensitive to the planets that are large and that orbit close to their stars, as these produce the deepest and the most frequent transits. But for the planets that it can find, it provides us with a unique and incredibly powerful tool for beginning to understand their true nature. It is a technique that is transforming exoplanet science from a field of simple demographic census-taking to a field of detailed physical and chemical characterization. It is a technique that is allowing us to move from just asking how many planets are there to asking the deeper and more profound question, what are these worlds actually like? The detection of phosphine in the upper temperate cloud decks of Venus, announced in 2020, was a scientific discovery that was as exciting as it was controversial. Phosphine is a simple and highly toxic molecule made of 1 phosphorus atom and 3 hydrogen atoms. And on Earth, it is a gas that is almost exclusively associated with life. It is produced by anaerobic, microbial life in oxygen-poor environments like swamps, landfills, and the digestive tracts of some animals. There are no known significant abiotic, geological, or photochemical process that can produce phosphine in the oxygen-rich environment of our own planet. So, to find this gas in the atmosphere of our nearest planetary neighbor was a tantalizing and deeply provocative discovery. It raised the incredible and almost unbelievable possibility that a form of aerial, microbial life might be thriving in the relatively temperate and potentially habitable cloud layers of Venus, a planet whose surface is a scorching and utterly inhospitable hellscape. The initial detection was made with ground-based radio telescopes, and it was a subtle and very difficult measurement. The claim was immediately, and rightly, met with a great deal of scientific skepticism. Other research groups have tried, and have so far failed. To independently confirm the detection, the data has been reanalyzed, and there is an ongoing and very healthy scientific debate about whether the signal is real, and if it is, whether it is truly from phosphine or from some other, more common and less exciting molecule like sulfur dioxide. But even if the detection of phosphine on Venus ultimately turns out to be a false alarm, the episode has been an incredibly valuable and deeply important one for the field of astrobiology. It has forced us to think in new and more creative ways about the nature of biosignatures. It has reminded us that the search for life may not just be a search for the familiar, like oxygen, but also for the strange, the unexpected, the anomalous. And it has highlighted the crucial importance of a deep and deeply interdisciplinary understanding of the full, and often complex, abiotic chemistry of a planet before we can ever hope to make a confident claim for a biological origin. The phosphine story is a beautiful and very public example of the scientific process in action. It is a story of a bold and exciting claim, of a rigorous and skeptical response, of a community of scientists working together to try and get to the truth. And it is a story that has reignited our interest in our own, often overlooked, planetary neighbor. Venus may not be a habitable world in the Earth-like sense, but it's thick and chemically complex. Atmosphere is a fascinating natural laboratory, a place where we can study the extreme limits of planetary evolution, and a place that may yet hold some deep and very surprising secrets. The search for phosphine on Venus is a powerful reminder that the quest to find life in the universe is a journey that must begin in our own backyard, with a deep and deeply humble understanding of the worlds that are closest to home. The comparative study of our two nearest planetary neighbors, Venus and Mars, provides a powerful and deeply instructive natural experiment in the science of planetary habitability. They are the control group in our quest to understand why the Earth is the way it is. All three planets are rocky, terrestrial worlds. They all formed in the same inner region of our solar system, from roughly the same initial inventory of raw materials. And yet, they have evolved along three dramatically and profoundly different paths. Venus, our sister planet in terms of size and mass, is a cautionary tale, a vision of what can happen when the greenhouse effect runs amok. It is a planet that likely had a more temperate and perhaps even water-rich past, but its closer proximity to the Sun and perhaps a more vigorous early volcanism pushed it over a climatic tipping point. Its oceans boiled away, its atmosphere became thick with carbon dioxide, and its surface became a scorching and utterly sterile wasteland. Venus is a vision of a planetary paradise lost, a powerful reminder of the fragile and perhaps precarious nature of our own terrestrial climate. Mars, on the other hand, is a story of a different kind of planetary failure. It is a smaller and less massive planet than the Earth, and it is a planet that likely had a more promising and more Earth-like past. The evidence for ancient liquid water on Mars is now overwhelming, from the vast dried-up river deltas and the shorelines of ancient lakes that we see from orbit to the water lane, sedimentary rocks that are being analyzed by our rovers on the ground. The early Mars was likely a warmer, wetter, and much more habitable world than it is today. But Mars is a planet that lost its way. Its smaller size meant that its interior cooled down more quickly, its dynamo shut down, and it lost its protective global magnetic field. And without this magnetic shield, the solar wind has, over the billions of years, stripped away the vast majority of its atmosphere, turning it into the cold, dry, and almost airless desert that we see today. Mars is a fossil, a planetary museum, a place where we can study the preserved, geological, and perhaps even biological records of a once more habitable world. The Earth, then, is the Goldilocks planet, the world that got it just right. It is large enough to have a geologically active interior and a protective magnetic field. It is at the right distance from the sun to have a stable and temperate climate, and it has been blessed with a living and planet-altering biosphere that has played a crucial and perhaps an essential role in maintaining its long-term habitability. The comparative study of Venus, of Earth, and of Mars is the foundational text of the new science of comparative planetology. It is a story that is written in the rocks, in the atmospheres, and in the very orbits of these three very different and very special worlds. And it is a story that provides us with the crucial ground truth, the intellectual framework that we will need as we begin to extend our gaze outwards to the thousands of other and even more diverse planetary systems that are scattered throughout the vast and beautiful tapestry of our galaxy. The seasonal changes on an exoplanet, the rhythmic and often dramatic shifts in its climate and its environment over the course of its year, are another powerful and deeply informative window into its potential for habitability. On Earth, our seasons are caused by the tilt of our planet's spin axis relative to our orbit around the Sun. And these seasons are the driving force behind many of the most fundamental and most beautiful rhythms of our living world. They are the engine of our global climate system, the driver of our weather patterns, the metronome that sets the tempo for the cycles of growth, of decay, and of renewal in our biosphere. The search for the signs of similar seasonal changes on an exoplanet is one of the most exciting and most challenging new frontiers in astrobiology. By observing a planet at different points in its orbit, we can look for the subtle, periodic variations in its brightness, in its color, and in its atmospheric spectrum that could be the signature of a dynamic and seasonally changing world. We can use the technique of phase curve analysis, for example, to create a crude, one-dimensional map of the planet's temperature as it rotates. By observing how this map changes over the course of the planet's year, we can look for the signs of a seasonal thermal wave, a wave of warmth that moves from one hemisphere to the other. This would be a powerful indication that the planet has a significant axial tilt, a feature that is thought to be crucial for creating a stable and more equitable global climate. We can also search for the seasonal changes in the composition of the planet's atmosphere. A planet with a living and photosynthetically active biosphere, like the Earth, should show a seasonal breathing, a periodic variation in the concentration of atmospheric carbon dioxide, as the plants in the northern and the southern hemispheres go through their annual cycles of growth and dormancy. The detection of such a seasonal carbon dioxide cycle in the atmosphere of a distant exoplanet would be an incredibly powerful and deeply suggestive biosignature. It would be a sign that we have found a world that is not just habitable, but is, in a very real and a very beautiful sense, alive. The search for seasonality on exoplanets is a long-term and very patient endeavor. It requires us to observe a planet not just once, but many, many times over the full course of its orbital period, which for a planet in the habitable zone of a sun-like star is about one Earth year. This is a challenge for our current and often oversubscribed telescopes. But it is a challenge that is at the very heart of our quest to find a true Earth-like analog. It is a search that is not just about finding a planet with the right static properties, but is about finding a world with the right dynamic rhythms, A world that is not just a place, but is a living, breathing, and seasonally changing home. Photochemistry, the science of chemical reactions that are driven by light, is another crucial and often overlooked player in the complex and deeply interconnected drama of an exoplanet's atmosphere. The light from a host star is not just a source of heat, it is also a powerful and often highly reactive chemical agent. The high-energy ultraviolet photons from a star can break apart the stable and often biologically important molecules in a planet's atmosphere, a process called photodissociation. This can be a destructive process, as we have seen in the context of atmospheric escape, but it can also be a creative one. The highly reactive molecular fragments that are produced by photodissociation can then go on to combine with other molecules to form new, and often more complex, chemical species. This is the engine of atmospheric photochemistry. On Earth, for example, the formation of the protective ozone layer is a photochemical process. And in the thick, hazy atmosphere of Saturn's moon Titan, the sun's ultraviolet light is constantly breaking apart the methane molecules, triggering a complex and wonderfully rich chain of photochemical reactions that is producing a whole zoo of complex and often life precursor organic molecules. The study of the photochemistry of an exoplanet's atmosphere is an essential part of our assessment of its potential for habitability. It is a process that can both create and destroy the very molecules that we are searching for as potential biosignatures. The oxygen that is produced abiotically by the photodissociation of water vapor is a classic example of a photochemical false positive for life. The ozone that is produced by the photochemistry of an oxygen-rich atmosphere, on the other hand, can be a powerful and confirming secondary biosignature. To untangle this complex, and often ambiguous, web of photochemical reactions, we need to have a detailed and very accurate model of the planet's atmosphere. We need to know its temperature, its pressure, its composition, and we need to have a detailed and very accurate measurement of the ultraviolet spectrum of its host star, as it is the high-energy photons that are the primary drivers of this chemistry. This is a challenging and deeply interdisciplinary task, but it is an essential one. It is the key to moving beyond a simple and often naive interpretation of our atmospheric data, and towards a more sophisticated, more nuanced, and more physically grounded understanding of the complex and often beautiful chemical stories that are being told in the atmospheres of other worlds. Comparative planetology, the science of understanding a planet by comparing it with other, and often very different, worlds, is one of the most powerful and most fruitful approaches in our modern scientific exploration of the cosmos. By studying the diverse and often strange family of planets and moons in our own solar system, we can begin to understand the different possible evolutionary pathways that a planet can take. And we can build a more general and more robust theoretical framework for understanding the worlds that we are now discovering around other stars. The comparison of the three rocky terrestrial planets in our own solar system, Venus, Earth, and Mars, is the foundational text of this new science. It is a story, as we have seen, of a Goldilocks planet that got it just right, and of two sister worlds that, for different reasons, took a wrong turn on the path to habitability. This single, three-planet experiment provides us with a powerful and deeply instructive set of ground truths that we can then use to interpret our observations of the thousands of other rocky exoplanets that we are now discovering. The same principle applies to the gas giant planets. By studying the atmospheres of Jupiter and Saturn, with their complex, banded cloud structures, their powerful jet stream winds, and their deep and often violent convective storms, We can begin to build the models that we will need to understand the atmospheres of the hot Jupiters and the other gas giant exoplanets that we are finding in such abundance around other stars. The icy moons of the outer solar system, like Europa and Enceladus, with their deep subsurface liquid water oceans, are another crucial and deeply exciting point of comparison. They are a powerful reminder that the habitable zone is not just about the surface temperature of a planet, and that life could potentially thrive in a wide range of different and often extreme environments. They are a call to a more open-minded and more imaginative approach to our search for life beyond Earth. The ultimate goal of comparative planetology is to move beyond the small and perhaps unrepresentative sample of worlds in our own solar system, and to build a true galactic-scale periodic table of planets. We want to be able to classify the thousands of exoplanets that we are now discovering, to understand their demographics, to identify the different families and species of worlds that exist in our galaxy. We want to be able to understand the relationship between a planet's properties and the properties of the star it orbits and the planetary system it is a part of. And in doing so, we want to be able to place our own solar system and our own precious and life-bearing Earth into its proper cosmic context. Is our solar system a typical or an unusual outcome of the planet formation process? Is a world like the Earth a common or a vanishingly rare phenomenon? These are some of the deepest and most profound questions that we can ask, and it is only through the powerful and deeply illuminating lens of comparative planetology that we can ever hope to find the answers. The detection of carbon dioxide in the atmosphere of an exoplanet is a discovery of immense and multifaceted scientific significance. It is a molecule that is a key player in the geology, the chemistry, and the climate of a rocky terrestrial planet. And it is a molecule that is deeply and inextricably linked to the processes of life as we know it. The presence of a significant amount of carbon dioxide in an exoplanet's atmosphere is, first and foremost, a powerful indicator of geological activity. On Earth, carbon dioxide is the primary gas that is released from volcanoes, and it is the key ingredient in the long-term carbonate-silicate cycle that acts as our planet's global thermostat. The detection of carbon dioxide on a rocky exoplanet would be a strong and deeply encouraging sign that the planet is geologically alive, a sign that it has a dynamic and potentially climate-stabilizing interior. Carbon dioxide is also a powerful greenhouse gas. Its presence in an atmosphere can trap heat, warming the planet and increasing its potential for maintaining liquid water on its surface by measuring the abundance of carbon dioxide in an exoplanet's atmosphere. And by combining this with our knowledge of the planet's orbit and its host star's brightness, we can begin to build the first realistic climate models for these distant worlds. We can start to ask the question of whether a planet is likely to be a temperate, watery world like the Earth, or a scorching, runaway greenhouse like Venus. And, of course, carbon dioxide is one of the most fundamental and most universal ingredients for life. It is the source of the carbon atoms that are the backbone of all the complex, organic molecules of biology. On Earth, the process of photosynthesis, which is the foundation of almost our entire global ecosystem, is a process of taking in carbon dioxide from the atmosphere and using the energy of sunlight to convert it into the sugars that are the fuel for life. The detection of carbon dioxide in the atmosphere of a potentially habitable exoplanet would be a sign that the fundamental raw material for a photosynthetic biosphere is present, and the detection of a seasonal and biologically driven variation in the concentration of this carbon dioxide would be one of the most powerful and most beautiful biosignatures that we could ever hope to find. The detection of carbon dioxide is now a routine and stunningly successful. Part of the work of the James Webb Space Telescope. It has been detected in the atmospheres of a number of different exoplanets, from the hot Jupiters to the smaller and potentially rocky super-Earths. Each of these detections is a new and deeply informative piece in the complex and endlessly fascinating puzzle of exoplanet science. And each of them is a step closer to the ultimate and most profound of all our exploratory goals, the discovery of a world that is not just like the Earth, but is a world that is, like the Earth, truly and wonderfully alive. The process of scientific discovery is not a simple, linear path from ignorance to truth. It is a messy, complex, and often frustrating process of gathering evidence, of building models, of testing hypotheses, and of constantly and rigorously questioning our own assumptions. And in the challenging and often data-starved field of exoplanet atmospheric science, the quest for reliable and robust findings is a particularly difficult one. The first and most fundamental step in ensuring the reliability of our findings is the data itself. We must have an almost perfect understanding of our instruments, of their limitations, of their sources of noise. We must have a sophisticated and highly robust data analysis pipeline that can take the raw, and often messy, data from the telescope and can process it, can calibrate it, and can extract the tiny, precious signal of the exoplanet's atmosphere from the overwhelming glare of its host star. This is a task that requires a deep and deeply collaborative effort between the engineers who build the instruments, the software developers who write the analysis code, and the scientists who ultimately use the data. The next step is the process of model fitting or retrieval. This is the process of comparing our observational data with the predictions of our theoretical atmospheric models. And here, too, the quest for reliability is a paramount and often challenging. 1. Our models are only as good as the assumptions that go into them. And in the field of exoplanet science, where we are often dealing with worlds that are very different from our own, we must be constantly vigilant about the potential for our own, often Earth-centric, biases to lead us astray. This is why it is so important to explore a wide range of different possible models, to be honest and transparent about the uncertainties and the degeneracies that are inherent in our analysis, and to avoid the temptation to overinterpret our often sparse and noisy data. The principle of independent verification is another, absolutely essential, part of the scientific process. A single, exciting result from a single telescope is not, in itself, a definitive discovery. It must be confirmed by other independent teams using other independent telescopes, and preferably other independent analytical techniques. This is how science builds a robust and reliable consensus. The process of peer review, where a scientific paper is scrutinized by other anonymous experts in the field before it is published, is a crucial part of this process of communal and critical self-correction. And finally, and perhaps most importantly, the quest for reliability requires a deep and abiding sense of intellectual humility. We must be willing to be wrong. We must be open to the possibility that our favorite theories, our most cherished models, are incorrect. We must be constantly and actively searching for the evidence that might contradict our own pre-existing beliefs. This is the very heart and soul of the scientific method, and it is a spirit that is more important than ever in a field like astrobiology, where the stakes are so high, and where the desire to find what we are looking for can be such a powerful and potentially blinding force. The search for life beyond Earth is a journey of immense and truly historic proportions, and it is a journey that we must undertake with the utmost scientific and intellectual integrity. The use of computer models is an absolutely indispensable tool in our modern scientific quest to understand the atmospheres of distant exoplanets. The data we receive from these worlds is, by its very nature, indirect, sparse, and often deeply ambiguous. It is the power of our models, the sophisticated and often beautiful interplay of physics, of chemistry, and of advanced computational techniques that allows us to translate this faint and often noisy data into a rich and scientifically meaningful story. The process is a beautiful and deeply iterative dance between theory and observation. We begin with a theoretical model of what a planet's atmosphere might be like. This forward model is a complex and deeply interdisciplinary piece of software. It contains our best current understanding of the fundamental physical and chemical processes that govern an atmosphere, the laws of thermodynamics, of fluid dynamics, of radiative transfer, of chemical kinetics. It contains a vast and meticulously compiled database of the spectral properties of all the different atoms and molecules that might be present in the atmosphere. We can then use this model to simulate a wide range of different possible atmospheres. We can vary the planet's temperature, its pressure, its composition, the presence or absence of clouds, and for each of these hypothetical atmospheres, the model can predict the specific observable signature that we would expect to see with our telescope. For example, the transmission spectrum during a transit. This creates a vast and incredibly rich library of theoretical possibilities. The next step is to compare these theoretical predictions with the actual observational data. This is the process of retrieval or inversion, and it is a process that is at the very heart of exoplanet atmospheric science. It is a complex and often computationally intensive statistical problem. We must search through the vast multidimensional parameter space of our models to find the specific combination of atmospheric properties that provides the best possible fit to our data. This is where modern machine learning techniques are becoming increasingly powerful. An AI can be trained on this vast library of simulated spectra, and it can learn the complex and often highly nonlinear relationship between the atmospheric parameters and the resulting observable signal. This allows it to rapidly and often very accurately invert a new observed spectrum, providing a fast and powerful way to estimate the properties of an exoplanet's atmosphere. But the story does not end there. The results of this retrieval process, the new and often surprising insights that we gain about the nature of these distant worlds, are then fed back into the development of our theoretical models. If we discover a planet with a chemical composition that our models cannot explain, it forces us to go back to the drawing board, to rethink our assumptions, to incorporate new, and perhaps more exotic, chemical or physical processes into our simulations. This is a beautiful and deeply creative feedback loop, a constant dialogue between the observed and the imagined, between the data and the theory. It is in this iterative and deeply collaborative process that our true and ever-deepening understanding of the wonderfully diverse and often surprisingly strange atmospheres of other worlds is born. The habitability of tidally locked exoplanets, worlds that are so close to their host star that they are in a state of synchronous rotation, with one side permanently facing the star and the other side permanently facing away, is one of the most fascinating and most actively debated topics in modern astrobiology. These are the most common type of potentially habitable planets that we are likely to find. As the habitable zones of the small, cool, and incredibly numerous red dwarf stars are very close in, a tidally locked planet is a world of extreme and permanent contrasts. It has a day side that is in a state of perpetual scorching sunlight, and a night side that is in a state of perpetual freezing darkness. At first glance, this would seem to be a deeply inhospitable environment for life. The day side could be hot enough to boil away any liquid water, while the night side could be cold enough to freeze the very atmosphere solid. But the planet's atmosphere can act as a powerful and potentially life-saving heat redistribution engine. If the atmosphere is thick enough, then strong, global winds would be set up, transporting heat from the hot day side to the cold night side. This could create a more temperate and more equitable global climate, with a band of potentially habitable twilight conditions in the region between the two extremes. The terminator zone, the nature of these winds, and the resulting climate is the subject of intense and often beautiful computer simulations. These models show that a tidally locked planet with a thick atmosphere could have a strange and very alien weather pattern, with a single, massive substellar cloud deck that is permanently parked on the day side, reflecting a significant portion of the incoming starlight and helping to keep the planet cool, and a system of strong planet-encircling winds that would create a relatively mild and stable climate on the night side. The composition of the atmosphere is also crucial. The presence of greenhouse gases, like carbon dioxide and water vapor, would be essential for trapping heat and for maintaining a warm enough temperature for liquid water to exist, particularly on the night side and in the terminator zone. The presence of a significant global ocean could also play a major and very beneficial role. The ocean currents would be another, very efficient, mechanism for transporting heat from the day side to the night side, further moderating the planet's climate. A tidally locked water world could be one of the most promising and most stable types of habitable environments in the galaxy. But there are also significant challenges. The intense and often violent stellar flares from a young red dwarf star could strip away the atmosphere of a close-in, tidally locked planet unless it is protected by a strong global magnetic field. And the lack of a day-night cycle could have a profound, and as yet unknown, impact on the evolution of any life that did manage to arise. The study of tidally locked exoplanets is a journey into a new and deeply strange territory of planetary science. It is a journey that is forcing us to abandon our Earth-centric biases and to think in new and more creative ways about the wonderfully diverse and often surprising forms that a habitable world might take. The distinction between a reducing and an oxidizing atmosphere is a fundamental concept in planetary science, and it is a distinction that is absolutely critical in our search for life beyond Earth. A reducing atmosphere is one that is rich in molecules that are eager to donate electrons in a chemical reaction. Molecules like hydrogen, methane, and ammonia. An oxidizing atmosphere, on the other hand, is one that is rich in molecules that are eager to accept electrons. Molecules like oxygen, carbon dioxide, and water vapor. The early Earth's atmosphere was a reducing one. And it was in this electron-rich, primordial soup that the complex organic molecules of life are thought to have been first synthesized. The Earth's modern atmosphere, on the other hand, is a strongly oxidizing one, a direct consequence of the 2.5 billion year long project of oxygenic photosynthesis by the planet's living biosphere. The redox state of a planet's atmosphere, the balance between its reducing and its oxidizing components, is therefore a powerful and deeply informative tracer of its geological, its chemical, and its potential biological history. To distinguish between these different types of atmospheres on a distant exoplanet, we must once again turn to the power of spectroscopy. By analyzing the transmission or the emission spectrum of a planet's atmosphere, we can search for the telltale chemical fingerprints of both the reducing and the oxidizing gases. The detection of a significant amount of methane in a planet's atmosphere, for example, would be a strong indication of a reducing environment. The detection of a significant amount of oxygen or ozone, on the other hand, would be a strong indication of an oxidizing one. But the most exciting and most powerfully life-indicating discovery would be the detection of both at the same time. The simultaneous presence of a significant amount of a reducing gas, like methane, and a significant amount of an oxidizing gas, like oxygen, is a profound and deeply suggestive state of chemical disequilibrium. It is a sign that there are two powerful and competing processes at work on the planet, one that is pumping out the reducing gas and one that is pumping out the oxidizing gas. And while there are some purely geological scenarios that could, in principle, create such a disequilibrium, the most plausible and most exciting explanation is the presence of a diverse and globally significant biosphere, a biosphere that contains both the methanogenic anaerobic life that produces methane and the photosynthetic aerobic life that produces oxygen. This is the ultimate redox biosignature, the holy grail of exoplanet atmospheric science. The search for this specific and deeply life-indicating chemical imbalance is one of the primary scientific goals of the James Webb Space Telescope. It is a search that is on the very edge of our current technological capabilities, but it is a search that holds the promise of a discovery that would be as profound as it would be beautiful. The discovery of a world that is not just habitable, but is a world that is, like our own, a complex and wonderfully imbalanced living planet. The weather on an exoplanet, the dynamic and often violent dance of its atmosphere, is another crucial and deeply informative aspect of its potential for habitability. A planet's climate, its long-term average weather, is what determines the overall environmental conditions on its surface. But it is the weather, the short-term and often unpredictable fluctuations in temperature, in pressure, in wind, in precipitation, that a living organism must actually endure and adapt to on a day-to-day basis. The study of exometeorology, the weather on other worlds, is a new and incredibly exciting frontier in planetary science, and we are just beginning to take our first tentative steps into this new and uncharted territory by observing a planet at different points in its orbit. As different parts of its surface rotate into and out of view, we can begin to create crude, global maps of its temperature and its cloud cover. We can look for the large-scale and often stable weather patterns, like the powerful jet stream winds that are thought to encircle the hot Jupiter exoplanets, or the persistent substellar cloud deck that is predicted to exist on the day side of a tidally locked world. We can also look for the more transient and more dynamic signs of weather, like the formation and the dissipation of clouds, or the passage of a large planetary-scale storm system. These are incredibly challenging observations, as they require us to detect the very small and often very subtle changes in a planet's brightness and color over time. But the rewards are immense. The presence of a dynamic and variable weather system is a powerful and deeply encouraging sign of a planet with a thick and active atmosphere. The detection of water cloud and of their periodic formation and precipitation would be an incredibly exciting discovery, a strong and deeply suggestive piece of evidence for the existence of a global and life-sustaining hydrological cycle. But extreme weather can also be a profound and often insurmountable challenge to a planet's habitability. A planet with a very thin atmosphere, or one that is very far from its star, might be subject to wild and life-prohibiting temperature swings between day and night. A planet that is orbiting a very active and volatile star might be subject to frequent and powerful space weather events, which could disrupt its climate and sterilize its surface. The study of the weather on other worlds is a journey that is forcing us to think in new and more sophisticated ways about the complex and often beautiful interplay between a planet's atmosphere, its climate, and its potential for life. It is a journey that is a powerful reminder that a habitable world is not just a static and unchanging object with the right, average properties. It is a dynamic, evolving, and often wonderfully stormy, living system. The story of an exoplanet's atmosphere is not a static one. It is a long, complex, and often dramatic evolutionary tale, a story that is shaped by a host of different and often competing physical and chemical processes over the course of the planet's entire multi-billion-year life. A planet is not born with the atmosphere that it will have for all of eternity. It is born with a primary atmosphere, a thick gaseous envelope that it accretes from the primordial, protoplanetary disk of its host star. This primary atmosphere is composed primarily of the most abundant elements in the universe, hydrogen and helium. The massive gas giant planets in our own solar system, like Jupiter and Saturn, were large enough and formed far enough from the Sun to be able to hold on to these thick primordial atmospheres. But the smaller, rocky, terrestrial planets, like the Earth, were too small, too hot, and too close to the Sun to be able to retain their primary atmospheres. They were likely lost to space in the first few 100 million years of the solar system's history, stripped away by the intense, high-energy radiation and the powerful stellar wind from the young and very active Sun. The atmosphere that we are breathing today is a secondary atmosphere, an atmosphere that was created later in the planet's history, primarily through the process of outgassing from volcanic eruptions. This secondary atmosphere was composed of the gases that were trapped in the planet's interior during its formation. Gases like water vapor, carbon dioxide, nitrogen, and sulfur compounds. This was a very different atmosphere than the one we have today. It was a thick, carbon dioxide-rich, and almost completely oxygen-free atmosphere. The transformation of this secondary atmosphere into the modern, nitrogen-oxygen-rich atmosphere of our own living world is the story of the third and most profound stage of atmospheric evolution, the co-evolution of the atmosphere with the planet's living biosphere. The rise of oxygen, as we have seen, was a direct and deeply transformative consequence of the evolution of photosynthesis. But life has shaped our atmosphere in a host of other, more subtle ways. The nitrogen that makes up almost 80% of our modern atmosphere, for example, is also a product of biological activity, of the complex and deeply ancient nitrogen cycle that is driven by the metabolic activity of a diverse range of different microbes. The story of an exoplanet's atmospheric evolution is the story of this complex and often contingent interplay between these three great forces: the initial conditions of the planet's formation, the subsequent geological and photochemical evolution of its secondary atmosphere, and the potential and profoundly transformative influence of a living and planet-altering biosphere. By studying the atmospheres of a wide and diverse range of different exoplanets, at a wide and diverse range of different ages, we can begin to piece together the different possible evolutionary pathways that a planet's atmosphere can take. We can begin to understand the key and often critical turning points in a planet's atmospheric history, and we can begin to understand the full and wonderfully complex story of how a barren, rocky world can, under just the right set of circumstances, be transformed into a beautiful, blue, and life-bearing planet, a world like our own. The spectral index, a seemingly obscure and technical parameter from the world of theoretical cosmology, is, in fact, one of the most powerful and most deeply informative clues that we have about the very first and most mysterious moments of our universe's existence. It is a number that is a direct and beautifully precise fingerprint of the process of cosmic inflation. To understand the spectral index, we must first return to the idea that the seeds of all the large-scale structure in our universe, the galaxies, the clusters the cosmic web, were born from the tiny quantum fluctuations in the inflaton field during the period of exponential expansion. A key prediction of the simplest models of inflation is that these primordial fluctuations should be very nearly, but not perfectly, scale invariant. A scale invariant spectrum is one where the amplitude of the fluctuations is the same on all scales. It is like white noise in the world of sound, a noise that has equal power at all frequencies. The spectral index, often denoted by the letter NS, is a measure of the deviation of the primordial spectrum from perfect scale invariance. A value of NS equals 1 corresponds to a perfectly scale invariant spectrum. A value of NSCS less than 1. A red-tilted spectrum means that the fluctuations have slightly more power on large scales than on small scales. A value of NS greater than 1. A blue-tilted spectrum means that the fluctuations have slightly more power on small scales. And what is truly remarkable is that different specific models of inflation make different and very precise predictions for the value of the spectral index. The simplest, slow-roll inflation models, where the inflaton field is slowly and gently rolling down a very flat potential, predict a spectral index that is slightly less than 1, a slightly red-tilted spectrum. The precise value of this tilt depends on the detailed and as yet unknown shape of the inflaton potential. By measuring the statistical properties of the temperature fluctuations in the cosmic microwave background, we can make a very precise and very powerful measurement of the spectral index of the primordial fluctuations, and what we have found is a stunning confirmation of the simplest inflationary models. The data from the Planck satellite, our most precise map of the CMB, gives a value for the spectral index of about 0.965 with a very small uncertainty. This is a number that is tantalizingly and statistically significantly different from 1. It is a direct and beautiful detection of the subtle, red-tilted signature that is the smoking gun of the simplest and most elegant models of cosmic inflation. The measurement of the spectral index is one of the great triumphs of modern precision cosmology. It is a testament to our ability to extract a single, powerful, and deeply informative number from the complex, and often noisy, tapestry of the cosmic microwave background. And it is a number that is a direct and wonderfully profound window into the physics of the very first and most mysterious moments of our universe's long and beautiful cosmic story. The relationship between the theory of cosmic inflation and the fundamental concepts of entropy and time is a deep, a subtle, and a profoundly fascinating one. As we have seen, the arrow of time, our powerful and seemingly universal experience of a unidirectional flow of time from a fixed past to an open future, is thought to be rooted in the second law of thermodynamics, the law of increasing entropy. The universe as a whole is evolving from a state of low entropy, of high order, to a state of high entropy, of high disorder. And the great and still unresolved mystery is why the universe began in such an incredibly low entropy state to begin with. Does the theory of inflation help to solve this fundamental past hypothesis puzzle? The answer is a complex and still debated one. In one sense, inflation seems to make the problem even worse. The process of inflation takes a tiny and potentially very high entropy patch of the early universe and stretches it to an enormous size, creating a vast, smooth, and seemingly very low entropy, and therefore very improbable starting point for the subsequent hot Big Bang evolution. And yet, in another, deeper sense, Inflation may be the key to the solution. The key lies in recognizing that the entropy of the universe is not just in its matter and its radiation. It is also, and overwhelmingly, in its gravitational field. A smooth, uniform, and unclumped gravitational field, like the one that is created by inflation, is actually a state of incredibly low gravitational entropy. A clumpy, high-contrast gravitational field, a universe full of black holes, is a state of incredibly high gravitational entropy. The British physicist Roger Penrose has argued that the second law of thermodynamics, in a cosmological context, is really a statement about the tendency of the universe's gravitational field to evolve from a state of smoothness to a state of clumpiness. And inflation is the perfect physical mechanism for creating the incredibly smooth, and therefore incredibly low entropy, initial gravitational state that is required to get the arrow of time started. In this picture, our universe is not a random and highly improbable fluctuation. It is a natural, and perhaps even an inevitable consequence of a physical process that naturally produces a low entropy and time asymmetric starting point. The relationship between inflation and the nature of time itself is another, deeply fascinating, area of speculation. In the standard, inflationary picture, the inflaton field is rolling down its potential in a time-like direction. The process of inflation is a process that is happening in time. But in some, more speculative, eternal inflation scenarios, the situation is reversed. The self-reproducing and eternal inflation of the meta-universe is the timeless and fundamental reality. And our own bubble universe, with its arrow of time and its increasing entropy, is just a temporary and localized fluctuation, an eddy in a much larger and perhaps timeless cosmic river. This is a vision of reality that is on the very edge of our current scientific and philosophical understanding, but it is a vision that is a powerful reminder that our intuitive and often deeply cherished notions of time, of entropy, and of the beginning of the universe itself may just be a partial, and perhaps even a parochial, feature of our own, local, and very special, cosmic home. The concept of the inflaton, the hypothetical scalar quantum field that is thought to be the engine of cosmic inflation, is one of the most important and most mysterious ideas in modern cosmology. It is the protagonist in our current best story of the origin of the universe, the entity that is responsible for creating the vast, smooth, and structured cosmos that we inhabit. And yet we have almost no idea what it is. The inflaton is not a particle in our standard model of particle physics. It is something new, something that lies beyond our current and very successful theory of the subatomic world. The properties of the inflaton field are, at present, only very weakly constrained by our cosmological observations. We know that its potential energy curve must have a very specific and very flat shape to allow for a sufficiently long period of slow-roll inflation. We know that the energy scale of this potential must be very high, far beyond the energies that we can probe in our terrestrial particle accelerators. And we know that the inflaton must have a specific, and as yet unknown, coupling to the particles of the standard model to allow for the process of reheating, the conversion of its energy into the matter, and the radiation of the hot Big Bang at the end of inflation. The quest to identify the inflaton, to connect the abstract, and largely phenomenological, concept of the inflationary field with a specific and well-motivated theory of fundamental particle physics is one of the great, and as yet unsolved, challenges in theoretical cosmology. There are a host of different and often competing candidate theories. In some models, the inflaton is a fundamental, new, and as yet undiscovered scalar particle. In others, it is a composite field made up of other more fundamental particles. In the context of string theory, the inflaton is often identified with the moduli fields that describe the size and the shape of the extra hidden dimensions of spacetime. In this picture, the process of inflation is the process of these extra dimensions relaxing to their stable, ground state configuration, and in some, more radical models. The inflaton is not a new field at all, but is identified with the Higgs field, the same field that is responsible for giving mass to the fundamental particles in the Standard Model. This Higgs inflation scenario is a particularly elegant and economical idea, but it requires a very specific and as yet unproven non-minimal coupling between the Higgs field and gravity. Distinguishing between these different and often highly speculative models is an incredibly challenging task, but there are a few subtle and potentially powerful observational clues that we can search for. The precise value of the spectral index of the primordial density fluctuations and its subtle running with scale can provide a powerful and discriminating test of different inflationary models. And the holy grail of observational inflationary cosmology is the detection of the faint and as yet unseen background of primordial gravitational waves that are predicted to be a generic and almost unavoidable consequence of the inflationary process. These gravitational waves are ripples in the fabric of space-time itself, and they are generated by the quantum fluctuations of the gravitational field during inflation. Their detection would be a direct and stunning confirmation of the inflationary paradigm. And the amplitude of these waves, the tensor to scalar ratio, is a direct measure of the energy scale of inflation, a measurement that would provide a crucial and deeply informative window into the physics of the universe at energies that are trillions of times higher than anything we can achieve on Earth. The search for these primordial gravitational waves through the subtle B-mode polarization patterns that they should have imprinted on the cosmic microwave background is one of the most exciting and most challenging quests in all of modern observational cosmology. And it is a quest that holds the promise of not just confirming our general inflationary picture of the early universe, but of finally, and for the first time, beginning to identify the true physical nature of the mysterious and wonderfully creative inflaton field itself. The story of cosmic inflation is a story that is told in the language of quantum field theory, the beautiful and profoundly successful theoretical framework that underlies our modern standard model of particle physics. And yet, it is a story that is also, and at its very core, a story about gravity, about the dynamics of space-time itself. The full and complete understanding of inflation, therefore, requires a theory that can seamlessly and consistently weave together these two great pillars of modern physics, a theory of quantum gravity. In the standard semi-classical treatment of inflation, we treat the inflaton field as a quantum field that is evolving on a classical and smoothly expanding space-time background that is described by Einstein's equations of general relativity. This is a powerful and remarkably successful approximation, one that has allowed us to calculate the detailed statistical properties of the primordial density fluctuations with a precision that can be compared with our high-precision cosmological observations. But this semi-classical approximation is, at its heart, an inconsistent one. It is a hybrid theory that treats one part of the system quantum mechanically and the other part classically. A full and truly fundamental understanding of inflation requires us to treat both the inflaton and the spacetime itself as quantum entities. This is a task that is on the very edge of our current theoretical capabilities. A theory of quantum gravity, like string theory or loop quantum gravity, would describe a very different and much stranger reality for the very earliest moments of the inflationary epoch. In this picture, space-time itself would be a quantum and fluctuating entity. The very concepts of a smooth background geometry, of a definite cosmic time, would likely break down. The beginning of inflation would not be a transition that happens in time, but would be a transition of time itself, a transition from a pre-geometric, and perhaps timeless, quantum gravitational state to the classical, and smoothly expanding space-time of our later universe. The primordial fluctuations that are the seeds of all cosmic structure would not just be fluctuations of the inflaton field, they would be the combined and deeply entangled quantum fluctuations of both the inflaton and the space-time geometry itself, the development of a full and predictive theory of quantum cosmology. A theory that can describe the quantum state of the entire universe is one of the greatest and most profound challenges in all of theoretical physics. It is a challenge that requires us to grapple with the deepest and most difficult conceptual problems in science. Problems like the nature of time, the role of the observer, and the very meaning of a law of physics in a quantum universe where all possible histories may be realized. The theory of inflation, then, is not just a successful and well-tested model of the early universe. It is also a powerful and deeply informative conceptual bridge, a bridge that is connecting the empirical and increasingly precise world of observational cosmology with the abstract and often deeply strange world of quantum gravity. It is in the subtle and beautiful details of the cosmic microwave background, in the statistical properties of the primordial fluctuations, that we may be finding our first, faint and deeply precious, observational clues to the nature of the quantum reality that underlies all of space, all of time, and all of existence itself. The story of cosmic inflation is not just a single, monolithic narrative. It is a rich and wonderfully diverse landscape of different and often competing theoretical models. While all inflationary models share the same basic idea of a period of super-accelerated exponential expansion in the early universe, they differ in the details of the physical mechanism that is thought to have driven this expansion. The simplest and most widely studied class of models are the slow-roll inflation models. In these models, as we have seen, the inflation is driven by a single scalar quantum field, the inflaton, that is slowly and gently rolling down a very flat potential energy curve. The flatness of the potential is what ensures that the inflation lasts for a sufficiently long time to solve the horizon and the flatness problems, and to generate the primordial density fluctuations that we observe. This is a beautifully simple and very powerful paradigm, and it is one that is in remarkable agreement with our current high-precision cosmological data. But there are other, and often more complex, possibilities. Fast-roll inflation is a scenario where the inflaton field rolls down its potential much more quickly. This would lead to a shorter and more violent period of inflation, and it would produce a different and potentially observable spectrum of primordial fluctuations. Hybrid inflation is a model that involves two different scalar fields. One field is responsible for the slow-roll inflation, while the other is responsible for bringing inflation to an end in a rapid waterfall-like phase transition. These models can often accommodate a wider range of initial conditions than the simple slow-roll models, and they can produce unique and potentially detectable signatures in the form of cosmic strings or other topological defects. Chaotic inflation, as we have seen, is a model that takes place in a much larger and more chaotic primordial universe, where the inflaton field has different random values in different regions of space. This leads to the picture of eternal inflation and the multiverse, and there are a host of other, more exotic, models that are based on the ideas of string theory, of extra dimensions, of modified gravity. Each of these different inflationary models makes its own, unique, and often very subtle, set of predictions for the detailed statistical properties of the primordial fluctuations. They predict a slightly different value for the spectral index, a slightly different amount of non-Gaussianity, and most importantly, a different and potentially detectable amplitude for the background of primordial gravitational waves. The quest to distinguish between these different inflationary models is one of the primary driving goals of modern observational cosmology. It is a quest that is pushing our observational capabilities to their very limits. The high-precision measurements of the cosmic microwave background from the Planck satellite have already allowed us to rule out a number of the simplest inflationary models. And the next generation of CMB experiments, which are specifically designed to search for the faint B-mode polarization signature of primordial gravitational waves, will provide an even more powerful and more discriminating test. This is a beautiful and deeply satisfying example of the scientific method at its very best. We have a powerful and well-motivated theoretical paradigm inflation that has made a number of bold and very specific predictions. And we are now, for the first time, in a position to test these predictions with a level of precision that can allow us to move beyond just confirming the general idea, and to start to distinguish between the different possible physical realities that could have given rise to our own very special and very beautiful cosmic home. The cosmic microwave background, that faint, ancient, and ever-present whisper from the dawn of time, is our most precious and most powerful fossil of the early universe. It is a snapshot of the cosmos when it was just 380,000 years old, a time when the universe first became transparent to light. And imprinted on this snapshot is a wealth of information about the conditions that prevailed in the very first and most mysterious moments of creation. The CMB is, to a first approximation, incredibly uniform. The temperature of this relic radiation is the same, to about 1 part in 100,000, in all directions in the sky. This is the powerful and beautiful evidence for the horizon-solving power of cosmic inflation, but it is in the tiny and beautifully patterned anisotropies, the subtle 1 part in 100,000 temperature fluctuations, that the true and deepest secrets of the early universe are revealed. These temperature fluctuations are a direct and fossilized picture of the primordial density fluctuations that were the seeds of all cosmic structure. The hotspots in the CMB map are the regions that were slightly denser and therefore slightly hotter in the early universe. The regions that would, over the subsequent billions of years, grow under the influence of gravity to become the great galaxy clusters of today. The cold spots are the regions that were slightly less dense, the regions that would become the vast, empty, cosmic voids. By studying the statistical properties of these fluctuations, their amplitude, their distribution of sizes, their specific and beautifully patterned correlations, we can test the predictions of our cosmological models with an incredible and ever-increasing precision. The power spectrum of the CMB, a plot of the amplitude of the temperature fluctuations as a function of their angular size on the sky, is one of the most important and most beautifully measured graphs in all of science. It shows a series of acoustic peaks, a harmonic series of resonances that are the signature of the sound waves that were propagating through the hot, dense plasma of the early universe. The precise position and the relative height of these peaks are a sensitive probe of the fundamental cosmological parameters of our universe, the total density of matter and energy, the abundance of normal baryonic matter, the amount of dark matter, the value of the cosmological constant. The CMB is, in this sense, the ultimate cosmic Rosetta Stone A single, beautiful, and information-rich fossil that has allowed us to decipher the fundamental cosmological recipe of our universe. And the overall shape of the power spectrum, the slight red-tilted deviation from a perfect scale-invariant form, is the smoking gun evidence for cosmic inflation. The CMB is not just a picture of the past, it is also a powerful and deeply informative backlight. As this ancient light has traveled towards us for 13.8 billion years, it has been subtly but measurably affected by all the matter and the energy that it has passed through. The gravitational pull of the large-scale structures in the universe has deflected the paths of the CMB photons, a phenomenon called gravitational lensing. By studying these subtle lensing distortions in our maps of the CMB, we can create a map of the distribution of all the mass, including the invisible dark matter, between us and the early universe. The CMB is a gift that keeps on giving. It is a single, beautiful, and endlessly rich source of information, a window that allows us to see and to understand our universe in a way that is as profound as it is beautiful. The Lyman Alpha Forest, a strange and beautifully complex feature in the spectra of distant quasars, is another powerful and deeply informative window into the structure and the evolution of the early universe. A quasar is an incredibly bright and very distant object, the luminous, active core of a young galaxy that is powered by a supermassive black hole. As the light from a distant quasar travels towards us across billions of light-years of intergalactic space, it passes through the tenuous and largely invisible clouds of neutral hydrogen gas that make up the cosmic web, the vast filamentary network of matter that fills the spaces between the galaxies. Each of these intervening hydrogen clouds will absorb the quasar's light at a specific and well-known ultraviolet wavelength, the Lyman alpha transition of the hydrogen atom. But because the universe is expanding, each of these clouds is at a different distance from us, and is therefore receding from us at a different speed. This means that the Lyman alpha absorption line from each cloud will be Doppler shifted to a different and longer wavelength. The result, in the spectrum of the quasar, is not a single absorption line, but a dense and seemingly chaotic forest of many different absorption lines, each one corresponding to a different intervening cloud of hydrogen gas. This Lyman alpha forest is a one-dimensional core sample of the cosmic web. By studying the distribution and the properties of these absorption lines, we can map the distribution of matter along the line of sight to the quasar. We can see the dense, filamentary structures where the absorption is strong, and the underdense, void-like regions where the absorption is weak. This allows us to study the statistical properties of the cosmic web at a time when the universe was just a few billion years old, a crucial and previously inaccessible epoch in the history of cosmic structure formation. And what we find is a stunning confirmation of our overall cosmological picture. The statistical properties of the Lyman alpha forest, the power spectrum of its density fluctuations, are in beautiful agreement with the predictions of our lambda cold dark matter model, the model that is based on a universe that is dominated by dark energy and cold dark matter, and whose initial seeds were laid down by the process of cosmic inflation. The Lyman alpha forest is a powerful and deeply satisfying piece of the cosmological puzzle. It is a bridge that connects the physics of the very early universe, as revealed by the cosmic microwave background, with the more mature and more structured universe of galaxies that we see around us today. It is a beautiful and wonderfully complex testament to the power of our cosmological models to explain the entire 14 billion year-long history of our universe, from the first, faint, quantum whispers of the inflationary epoch to the vast and wonderfully intricate cosmic tapestry of the present day. The story of cosmic evolution is a story that is written not just in the language of physics, but also in the language of topology, the mathematical study of shape and connectivity. The cosmic topology is the overall, large-scale shape and structure of our universe, and the theory of cosmic inflation has a profound and deeply interesting relationship with this fundamental, geometric property of our reality. As we have seen, one of the great triumphs of inflation is its ability to explain the observed, and otherwise very puzzling, flatness of our universe. But flat does not necessarily mean infinite. The surface of a cylinder or of a torus is also, in a mathematical sense, flat. An observer on the surface of such a space would find that the rules of Euclidean geometry hold true, that parallel lines never meet, that the angles of a triangle always add up to 180 degrees. And yet, these are finite spaces. If you were to travel in a straight line on the surface of a torus, you would eventually return to your starting point. It is possible, then, that our own three-dimensional universe is both flat and finite. It could have the topology of a three-torus, a three-dimensional version of the donut shape, where if you travel far enough in any direction, you will loop back around and return to where you started. This would be a universe that is finite in volume, but has no edge, no boundary. The search for the signature of such a multi-connected topology is one of the most exciting and most challenging quests in modern observational cosmology. If our universe were a three-torus, and if its size were smaller than the size of our observable universe, then we should be able to see the evidence of this in our maps of the cosmic microwave background. We should be able to see the same characteristic patterns of temperature fluctuations repeating themselves on opposite sides of the sky. It would be like living in a cosmic hall of mirrors. The search for these repeating circles in the sky patterns in the Planck data has been a major and very challenging area of research. So far, no definitive and statistically significant evidence for such a non-trivial topology has been found. This means that if our universe is a three-torus, its fundamental size must be larger than the size of our observable horizon. But the search continues. The theory of inflation also has a deep and potentially observable connection to the topology of the multiverse. In the eternal inflation scenario, our universe is just one bubble universe in a vast, and perhaps infinite, foam of other bubbles. The collision of our bubble with another in the distant past could have left a detectable topological scar on our cosmos, a circular region of the cosmic microwave background with anomalous statistical properties. The search for these bubble collision signatures is another very active and very exciting area of research. It is a search that is on the very edge of our observational capabilities. But it is a search that holds the promise of a discovery that would be as profound as it would be beautiful. The first, tentative, and deeply tantalizing piece of observational evidence for the existence of a reality that lies beyond our own, beautiful, and perhaps not so lonely, cosmic home. The story of cosmic evolution. From the first, faint, quantum whispers of the inflationary epoch to the vast and wonderfully complex cosmic web of galaxies that we see today, is a story that is, at its heart, a story of the growth of structure. It is the story of how a universe that began in a state of almost perfect and almost featureless uniformity was able to give rise to the rich and beautifully patterned tapestry of the modern cosmos, and the theory of cosmic inflation is the key that has unlocked our understanding of this profound and deeply creative cosmic process. The seeds of all the structure in our universe were sown during the first infinitesimal fraction of a second of its existence. They were the tiny and unavoidable quantum fluctuations in the inflaton field, the field that was driving the exponential expansion of the universe. These quantum fluctuations, which are an intrinsic and deeply mysterious feature of the quantum vacuum itself, were stretched by the immense inflationary expansion from their natural subatomic scale to macroscopic and even astronomical scales. This process froze these quantum fluctuations into a set of classical and very real density perturbations, a faint and almost perfectly scale invariant pattern of slightly overdense and slightly underdense regions that was imprinted on the very fabric of the young and rapidly expanding space-time. At the end of inflation, when the energy of the inflaton field was converted into the hot, dense plasma of the Big Bang, these primordial density fluctuations became the initial conditions for all subsequent cosmic evolution. The regions that were slightly denser had a slightly stronger gravitational pull. And in the subsequent billions of years of the universe's expansion, this process of gravitational instability would do its slow, patient, and inexorable work. The rich would get richer. The slightly overdense regions would begin to gravitationally attract the matter from their surrounding, less dense regions. This would cause them to grow, to become more and more overdense, their gravitational pull becoming stronger and stronger in a self-reinforcing runaway process. It was in these collapsing and ever-densing regions that the first and then the subsequent generations of stars and galaxies would be born. The slightly underdense regions, on the other hand, would become the great and largely empty cosmic voids. The result of this 14 billion year-long process of gravitational collapse and evolution is the beautiful and wonderfully intricate cosmic web that we see today, a vast, interconnected network of dense, galaxy-rich filaments and clusters surrounding the vast and largely empty cosmic voids. The statistical properties of this cosmic web, the size distribution of the clusters, the spacing of the galaxies, the shape of the filaments are a direct and fossilized reflection of the statistical properties of the primordial quantum fluctuations that were laid down during inflation. And what is truly remarkable and deeply satisfying is that the statistical properties of the cosmic web that we observe in the local and more mature universe are in perfect and stunningly precise agreement with the statistical properties of the primordial fluctuations that we observe in the faint ancient light of the cosmic microwave background. This is a beautiful and incredibly powerful confirmation of our entire cosmological story. It is a story that connects the largest structures in our universe with the smallest and most mysterious of all quantum phenomena. It is a story that tells us that we are all, in the most literal and most profound sense, the children of the quantum void. The story of cosmic inflation, while a beautiful, an elegant, and a remarkably successful theoretical paradigm, is not without its critics, its challenges, and its deep, and as yet unanswered, questions. One of the most persistent and most profound of these is the question of the initial conditions for inflation itself. The theory of inflation does a beautiful job of explaining how a small and potentially very strange patch of the early universe can be stretched into the vast, smooth, and flat universe that we observe today. But it does not, in itself, explain where this initial inflating patch came from. What was the state of the universe before inflation? And how did inflation get started in the first place? This is a question that pushes us to the very edge of our current physical understanding, into the realm of quantum gravity. Another related challenge is the problem of the trans-Planckian fluctuations. The primordial density fluctuations that are the seeds of all cosmic structure began their life as tiny quantum fluctuations with a wavelength that was, at the beginning of inflation, much, much smaller than the Planck length, the fundamental and seemingly indivisible quantum of distance itself. This is a deep and deeply troubling problem. It suggests that our current semi-classical theory of inflation, which is based on the idea of a smooth, continuous space-time, may be breaking down at its very foundations. A full and truly consistent understanding of the origin of these fluctuations will likely require a full theory of quantum gravity, a theory that can tell us about the nature of space and time at these ultimate and most mysterious of all scales. The theory of inflation also faces a number of challenges from the world of observation. While its generic predictions of a flat universe with a nearly scale-invariant spectrum of primordial fluctuations have been stunningly confirmed, the more specific predictions of the simplest and most elegant inflationary models have begun to come under some tension from our increasingly precise cosmological data. The Planck satellite, for example, has found a number of subtle and as yet unexplained anomalies in the cosmic microwave background on the very largest angular scales, features that do not seem to be a good fit to the predictions of the simplest inflationary models, and the search for the smoking gun of inflation, the faint and as yet undetected background of primordial gravitational waves, has, so far, come up empty. The non-detection of these gravitational waves has already allowed us to rule out a number of the simplest and most well-motivated inflationary models. And if these waves are not detected by the next generation of more sensitive CMB polarization experiments, it will place a severe and perhaps even a fatal constraint on the entire inflationary paradigm. This has led a number of prominent and highly respected cosmologists to begin to explore a range of different alternative to inflation theories that can try and solve the puzzles of the Big Bang without invoking a period of super-accelerated exponential expansion. These include the bouncing and the cyclic universe models that we have already discussed, as well as a number of other, more exotic ideas. This is a healthy and a necessary part of the scientific process. Inflation is, at present, our best and most well-supported theory of the very early universe, but it is not, and it should not be, the only game in town. The ongoing and often very lively debate between the proponents of inflation and the advocates for these alternative theories is a beautiful and deeply important example of science at its very best. It is a debate that is pushing our theories to their limits, that is inspiring a new generation of more precise and more powerful experiments, and that will, in the end, lead us to a deeper, a richer, and a more true understanding of our own beautiful and wonderfully mysterious cosmic origins. The concept of eternal inflation, the idea that our universe is just one bubble in a vast and eternally self-reproducing multiverse, is one of the most profound, most beautiful, and most deeply unsettling ideas in all of modern science. It is an idea that takes the logic of cosmic inflation to its ultimate and seemingly unavoidable conclusion, and it is an idea that has the power to fundamentally and irrevocably reshape our understanding of our own cosmic significance. In the standard inflationary picture, the process of inflation is a temporary and finite event. But in the chaotic and the eternal inflation scenarios, pioneered by André Linde, the process of inflation, once it starts, is a runaway and self-perpetuating. 1. The quantum fluctuations in the inflaton field are not just a source of the density perturbations that seed the galaxies. They are also a source of new and ever-expanding regions of inflating spacetime. The inflationary fire is a fire that can never be fully extinguished. It is a process that has no end, and in a sense, no beginning. It is a timeless and eternal cosmic engine of creation. And our own bubble universe, with its hot Big Bang, its 14 billion years of evolution, and its own unique set of physical laws, is just one, fleeting and localized, product of this endless cosmic froth. This is a vision of reality that is almost impossible for our finite human minds to fully grasp. It is a vision of a cosmos that is not just large, but is truly and staggeringly infinite. And it is a vision that has a number of profound and deeply important philosophical implications. It provides, as we have seen, a natural and scientifically motivated framework for the anthropic principle. But it also raises a number of deep and very difficult conceptual and mathematical challenges. One of the most profound of these is the measure problem. If the multiverse is infinite, and if it contains an infinite number of every possible type of event, then how can we ever hope to make a meaningful, probabilistic prediction? In an infinite multiverse, anything that can happen will happen. And it will happen an infinite number of times. This makes it very difficult to say that one outcome is more likely than another. To make sense of this, we need to find a way to regulate these infinities, a way to define a sensible, mathematical measure on the infinite set of all possible events. This is a deep, and as yet unsolved, problem in theoretical physics, and it is a problem that is at the very heart of our attempts to turn the beautiful and deeply compelling idea of the multiverse into a truly predictive scientific theory. The search for the observational signatures of eternal inflation is another, major and very challenging frontier. As we have seen, the detection of a cosmic bruise from a collision with another bubble universe would be a stunning and truly revolutionary discovery. The search for the subtle and potentially detectable effects of the multiverse on the values of our own fundamental constants is another exciting and very speculative avenue of inquiry. But even in the absence of such a definitive smoking gun detection, the idea of eternal inflation is a powerful and deeply transformative one. It is an idea that forces us to confront the true and almost unimaginable scale of reality. It is an idea that challenges our deepest and most cherished notions of our own human uniqueness, and it is an idea that presents us with a new and profoundly humbling vision of our place in the cosmos. A vision of ourselves as the inhabitants of a single and perhaps very ordinary island in a vast, beautiful, and eternally creative cosmic archipelago, the Lyman Alpha Forest, that beautiful and wonderfully complex lacework of absorption lines in the spectra of distant quasars, is more than just a powerful and confirming piece of evidence for our standard cosmological model. It is also a rich and increasingly precise laboratory for studying the subtle and often very challenging physics of the intergalactic medium, the tenuous and largely invisible web of gas that fills the vast spaces between the galaxies. By studying the detailed statistical properties of the Lyman Alpha Forest, we can learn about the temperature, the density, and the ionization state of the cosmic web at a time when the universe was just a few billion years old. This allows us to test our detailed and often very complex hydrodynamical simulations of the formation of cosmic structure. It allows us to study the process of reionization, the epoch when the light from the first stars and quasars heated and ionized the neutral hydrogen gas that filled the early universe. And it allows us to place powerful and deeply important constraints on the properties of some of the most mysterious and most fundamental components of our universe. The Lyman Alpha Forest, for example, is a very sensitive probe of the nature of dark matter. If dark matter were warm, if its particles had a significant thermal velocity in the early universe, then it would be more difficult for it to clump together on small scales. This would have the effect of smoothing out the small-scale structure of the cosmic web, and it would leave a detectable and very specific signature in the statistical properties of the Lyman alpha forest. The fact that we do not see this signature in the observational data from the forest has allowed us to place some of the strongest and most robust constraints on the properties of warm dark matter, and to provide powerful and deeply important support for the standard cold dark matter paradigm. The Lyman alpha forest is also a powerful and surprisingly sensitive probe of the nature of neutrinos. Neutrinos, as we have seen, are very light and very weakly interacting particles, but there are a lot of them in the universe, and because they are so light, they were moving at close to the speed of light in the early universe. This means that they, too, would have had the effect of smoothing out the small-scale structure of the cosmic web. By carefully measuring the power spectrum of the Lyman alpha forest, and by comparing it with the predictions of our cosmological models, we can place a powerful and very important constraint on the total, and as yet unknown, mass of the three different types of neutrinos. This is a beautiful and deeply satisfying example of the profound and often surprising interconnectedness of modern fundamental physics. It is a story of how the study of the largest and most diffuse structures in our universe can provide us with some of the most precise and most powerful information about the properties of the smallest and most elusive of all subatomic particles. And it is a story that is a testament to the incredible and ever-increasing power of our cosmological observations to probe the deepest and most fundamental secrets of nature. The story of the cosmic microwave background and its relationship to the theory of cosmic inflation is one of the most beautiful, most powerful, and most triumphant stories in the entire history of science. It is a story of a bold and deeply speculative theoretical prediction that was later confirmed with a stunning and ever-increasing precision by a series of beautiful and technologically audacious experiments. The CMB, as we have seen, is the faint and beautifully uniform afterglow of the Big Bang, but it is not perfectly uniform. Imprinted on this ancient light is a faint and wonderfully patterned tapestry of tiny, 1 part in 100,000 temperature fluctuations. And it is in these fluctuations that the story of cosmic inflation is written. The theory of inflation, in its simplest and most elegant form, makes a number of very specific and very testable predictions for the statistical properties of these fluctuations. It predicts that they should be Gaussian, that they should have a random bell curve-like distribution. It predicts that they should be adiabatic, that they should be fluctuations in the total energy density of the early universe, and not in the relative densities of the different particle species. And, most importantly, it predicts that their spectrum should be very nearly, but not perfectly, scale invariant. The measurements of the CMB from the COBE, the WMAP, and the Planck satellites have confirmed each of these predictions with a stunning and deeply satisfying precision. This is an incredible and truly historic triumph for the inflationary paradigm, but the CMB holds the promise of an even deeper and more powerful test of inflation. The theory predicts that the quantum fluctuations of the early universe should have generated not just the scalar density perturbations that are the source of the temperature fluctuations, but also a background of tensor perturbations, a background of primordial gravitational waves. These gravitational waves would have left their own unique and very subtle fingerprint on the CMB in the form of a specific and very faint, swirling, B-mode pattern in the polarization of the CMB light. The detection of these primordial B-mode polarization patterns is the holy grail of modern observational cosmology. It would be a direct and stunning smoking gun confirmation of the inflationary paradigm. And it would do even more. The amplitude of these B-modes is a direct measure of the energy scale of inflation. By measuring this amplitude, we would be able to, for the first time, take a direct and deeply informative Look at the physics of the universe at energies that are trillions of times higher than anything we can probe on Earth. It would be a window into the world of grand unification, the world where the fundamental forces of nature are thought to merge into a single, unified whole. The search for these primordial B-modes is an incredibly challenging and deeply heroic, experimental endeavor. The signal is expected to be incredibly faint, buried in a sea of foreground contamination from the polarized microwave emission of the dust in our own Milky Way galaxy. But a number of new and highly sensitive ground-based and balloon-borne experiments, like the Simons Observatory and the CMB-4 project, are now being built to take on this challenge. And it is a challenge that is at the very heart of our quest to understand our own cosmic origins. It is a quest to see, for the first time, the faint and wonderfully beautiful echo of the quantum gravitational birth of our own, very special, cosmic home. The concept of time, which seems so simple and so intuitive in our everyday lives, is, in the context of modern cosmology, one of the most profound, most mysterious, and most deeply challenging of all scientific and philosophical ideas. The theory of relativity, as we have seen, has taught us that time is not an absolute, universal, and unchanging metronome. It is a relative, a personal, and a malleable experience, a rhythm that is shaped by the dance of motion and of gravity. And the second law of thermodynamics has taught us that time has an arrow, a unidirectional flow that is rooted in the universe's inexorable and still mysterious journey from a state of low entropy to a state of high entropy. But what is time? At its most fundamental level, is it a true and irreducible feature of reality, or is it an emergent phenomenon, an illusion that arises from a deeper, and perhaps timeless, underlying reality? This is a question that lies at the very heart of the search for a theory of quantum gravity. In both general relativity and quantum mechanics, time plays a special and very different role. In general relativity, time is a dimension, a coordinate, a part of the dynamic and geometric fabric of space-time. In quantum mechanics, on the other hand, time is an external and absolute parameter, a classical background clock against which the probabilistic quantum drama unfolds, a full and consistent. Theory of quantum gravity must find a way to reconcile these two very different conceptions of time. And many of the leading approaches to this problem, like loop quantum gravity and some versions of string theory, seem to suggest that, at the most fundamental, Planck scale level, time as we know it may not exist at all in the Wheeler-DeWitt equation, the central and as yet unsolved equation of quantum cosmology. The variable for time simply disappears. The fundamental reality in this picture is a timeless and static wave function of the universe, a vast and eternally existing superposition of all possible three-dimensional geometries. The flow of time, in this view, is an emergent and perhaps an illusory phenomenon, a feature of our own classical macroscopic perception of this timeless quantum reality. This is a radical and deeply counterintuitive idea. But it is an idea that has a strange and beautiful resonance with the insights of many of the world's contemplative and mystical traditions, which have long taught that our normal linear experience of time is a product of our own limited human mind, and that it is possible, through deep meditative practice, to experience a more timeless and more fundamental state of being, a state of the eternal now. The quest to understand the ultimate nature of time is a journey that is on the very frontier of our scientific, our philosophical, and our spiritual inquiry. It is a journey that is forcing us to question our most basic and most cherished assumptions about the nature of reality. And it is a journey that is a powerful reminder that the universe is not just stranger than we imagine, but is likely stranger than we can imagine. A universe where the most familiar and most fundamental aspect of our own lived experience may be the deepest and most beautiful of all cosmic illusions. The story of cosmic evolution, as we currently understand it, is a story that is not just about the evolution of matter and of energy, but is also a story about the evolution of information. The universe, in its very first moments, was a state of incredible simplicity, a hot, dense, and almost perfectly uniform plasma. It was a state that could be described by a very small amount of information. But as the universe expanded and cooled, as the primordial, quantum fluctuations grew into the complex and wonderfully intricate tapestry of the cosmic web, the informational content of the universe has been constantly and dramatically increasing. Life itself is the most profound and most beautiful example of this informational complexification. A living organism is not just a complex chemical system, it is also a complex and wonderfully sophisticated information processing system. The genetic information that is encoded in the DNA of a single bacterium, for example, is more than 1 billion bits, a library of information that has been written and edited by 4 billion years of Darwinian evolution, and the information that is processed by a single human brain is of a complexity that is almost beyond our ability to comprehend. This informational arrow of time, this tendency of the universe to evolve from a state of low complexity to a state of high complexity, is a deep and as yet not fully understood aspect of our cosmic story. It is a story that seems to be in a strange and beautiful tension with the thermodynamic arrow of time, the tendency of the universe to evolve towards a state of greater disorder, of greater entropy. How can these two seemingly contradictory arrows coexist? The answer lies in the subtle and often beautiful interplay between entropy, information, and gravity. A living organism is a localized and temporary island of incredible order and low entropy. But it can only maintain this order by constantly taking in high-quality, low-entropy energy from its environment and by expelling low-quality, high-entropy waste heat back into the environment. The overall entropy of the system is always increasing, in perfect accordance with the second law of thermodynamics. Life, in this sense, is a beautiful and wonderfully creative process of surfing the thermodynamic arrow of time, of creating localized pockets of order and information in the midst of a universe that is, on the whole, running down, and gravity plays a crucial and often overlooked role in this process. As we have seen, in a gravitational system, the clumping of matter into more ordered structures, like stars and galaxies, is a process that actually increases the overall gravitational entropy of the universe. Gravity, in a sense, is the engine that drives the creation of the complex and information-rich structures that are the necessary precondition for the emergence of life. The story of our universe, then, is a story of a deep and wonderfully creative interplay between these two great arrows of time. It is a story of a universe that is, on the one hand, slowly and inexorably sliding towards a state of final and featureless heat death. But it is also a story of a universe that is, on the other hand, constantly and beautifully creating new and ever more complex pockets of order, of information, of life, of consciousness. And we, as conscious, living, and information processing beings, are the most profound and most beautiful expression of this creative and deeply informational cosmic story. The future of cosmology is a future that is not just about building bigger telescopes and more sensitive detectors. It is also a future that will be defined by our ability to ask new and more profound questions. Questions that are often on the very edge of our current scientific and philosophical understanding. What is the ultimate fate of our universe? Will it expand forever in a cold and lonely Big Freeze? Will it be torn apart in a violent and final Big Rip? Or will it, perhaps, one day, bounce back in a big crunch and be reborn in a new and endlessly repeating cosmic cycle? What is the ultimate nature of dark matter and of dark energy, the mysterious and dominant components of our universe? Are they new and as yet undiscovered particles and fields? Or are they a sign that our understanding of gravity itself is incomplete? What is the ultimate nature of the Big Bang? Was it the true and absolute beginning of time, or was it just a transition, a violent but ultimately local event in a much larger and perhaps eternal multiverse? And what is the ultimate nature of the laws of physics themselves? Are they a fixed and unique set of principles that are woven into the very fabric of reality? Or are they just the contingent and accidental bylaws of our own local cosmic neighborhood? These are the big and deeply challenging questions that will drive the field of cosmology in the 21st century. And they are questions that will require not just new and more powerful observations, but also new and more radical theoretical ideas. They are questions that will force us to push the boundaries of our current and very successful theories of relativity and quantum mechanics, and to search for a new and more unified the theory of quantum gravity. And they are questions that will inevitably lead us back to the deepest and most profound of all philosophical and existential questions, the question of our own human place in this vast, beautiful, and deeply mysterious cosmic story. The journey to understand the origin and the evolution of the universe is a journey that is, in the end, a journey to understand ourselves. It is a journey that is driven by a deep and uniquely human impulse, the impulse to know, to understand, to find meaning in the face of an otherwise silent and seemingly indifferent cosmos. And it is a journey that is, in its very nature, an endless one. For every new discovery we make, for every new horizon we cross, we will inevitably find a new and even deeper set of questions waiting for us on the other side. This is not a cause for frustration. It is the very source of the joy and the beauty and the endless creative vitality of the scientific enterprise. And it is a journey that we are all, in our own small and yet profoundly significant way, a part of. The consciousness that is now, in this quiet moment, contemplating the vastness of the cosmos, is the same consciousness that is the universe's own, beautiful and endlessly curious way of knowing itself. The part of the moon we never see from Earth, perpetually turned away and cloaked in darkness, has been a source of profound mystery for most of human history. For millennia, we had no direct knowledge of what lay on this hidden hemisphere. There were no landings, no close-up images, only the vast and silent canvas of the unknown. That all changed with the dawn of the space age. NASA, driven by an insatiable curiosity and the geopolitical imperatives of the Cold War, began to send missions, orbiters, and a suite of high-technology instruments to explore this enigmatic territory. What these robotic emissaries found was a world that was both alien and familiar, a landscape of stark and beautiful desolation. They discovered massive craters, the scars of ancient and violent impacts that shaped the early solar system. They detected strange and unexpected mineral compositions that did not seem to match anything in the moon's more familiar near-side geology. They picked up faint, ghostly magnetic signals, the fossilized remnants of a long-dead global magnetic field, a field that was unexpectedly strong and whose origins remain a source of intense scientific debate. And in the deep, frigid, and permanent shadows of the polar craters, they found the most precious and unexpected treasure of all definitive signs of frozen water. The far side is a place that, on the surface, looks dead and inert, a silent and unchanging world. But something about it, the sum of all these strange and disparate clues, does not quite add up. So, what is really out there on the far side of the moon, and why, after more than half a century of exploration, does it continue to hold such a powerful and enduring fascination for NASA and for the entire scientific community? The moon, our closest and most constant celestial companion, presents a single, familiar face to the Earth. For as long as humanity has gazed up at the night sky, we have seen the same unchanging patterns of dark, volcanic plains and bright, cratered highlands. This remarkable constancy is not a trick of light or distance. It is a fundamental and beautiful consequence of celestial mechanics, a phenomenon known as tidal locking. Understanding this gravitational dance is the key to grasping why one entire hemisphere of the moon remained utterly hidden from human eyes for countless millennia. A vast and mysterious territory shrouded in an enduring enigma that only the advent of modern spaceflight could finally unravel. Tidal locking is the end result of a long and patient gravitational conversation between a large primary body, in this case the Earth, and a smaller orbiting body, the Moon, over an immense and almost unimaginable span of cosmic time. The Earth's powerful gravitational pull has sculpted and shaped the Moon's rotation. The Moon is not a perfect, uniform sphere. It has slight, almost imperceptible bulges, both on the side that faces the Earth and on the opposite, far side. These bulges are a direct consequence of the Earth's gravity, which pulls more strongly on the near side of the Moon than on its center, and more strongly on its center than on its far side. This differential gravitational pull stretches the Moon slightly, like a piece of cosmic taffy, along the line connecting the two celestial bodies. In the early, chaotic history of the solar system, the Moon likely spun on its axis much faster than it does today. As it orbited the Earth, these tidal bulges would have been constantly slightly out of alignment with the direct Earth-Moon line. The Earth's immense gravity would have relentlessly tugged on these misaligned bulges, trying to pull them back into alignment. This constant, gentle tug created a torque, a rotational force on the Moon, which acted as a powerful and inescapable brake over hundreds of millions, and perhaps even billions, of years. This braking effect continued. The Moon's rotational energy was slowly dissipated, converted into a minuscule amount of heat through the internal friction of its own churning, rocky interior. This process was a one-way street, a relentless and irreversible journey towards a state of minimum energy, a state of perfect gravitational equilibrium. This equilibrium state is achieved when the Moon's period of rotation on its own axis precisely matches its period of revolution around the Earth. In simpler terms, the Moon now takes the exact same amount of time, about 27.3 Earth days, to spin around once as it does to complete one full orbit around our planet. This synchronized celestial waltz means that the same hemisphere of the Moon is perpetually and gracefully oriented towards the Earth. From our vantage point, it can appear as though the Moon is not rotating at all, but it is. Its spin is just perfectly and beautifully matched to its orbital speed. This is a common fate for large moons orbiting close to massive planets throughout our solar system and beyond. It is the natural, and often inevitable, outcome of a long and patient gravitational embrace. While it is true that the same side of the moon generally faces the Earth, a series of subtle and beautiful wobbles, known as librations, allow us to peek, just slightly, around its edges over the course of a lunar month. These librations are caused by the fact that the moon's orbit is not a perfect circle, but a slight ellipse, and its axis of rotation is slightly tilted. This means that, over time, a keen-eyed observer on Earth can actually see about 59% of the moon's surface. But that still leaves a vast and tantalizing 41% of our nearest celestial neighbor, a territory larger than the continent of Africa. That is forever and completely hidden from our direct line of sight. It is this large, truly hidden portion of the moon that constituted one of the great and most enduring mysteries of pre-space age astronomy. For thousands of years, the far side was a blank canvas, a realm of pure, scientific, and imaginative conjecture. No telescope, no matter how powerful, could bend light around the limb of the moon to reveal its unseen hemisphere. From the first, rudimentary spyglasses of Galileo Galilei in the 17th century, which revealed the moon to be a world of mountains and craters, to the massive, ground-based observatories of the 20th century. Every instrument was fundamentally limited by the moon's tidally locked orientation. This lack of direct observation meant that our maps of the moon were, by their very nature, incomplete. They represented only the visible half of a world, leaving the other side to the realm of artists' imaginings and educated, but ultimately unprovable, scientific guesses. The true and only. Reason for this prolonged mystery was the absence of a single, crucial technological leap space travel. Until the mid-20th century, the concept of sending a robotic probe, let alone a human being, beyond the Earth's atmosphere was confined to the pages of science fiction. The engineering challenges were immense, the stuff of dreams, but the dawn of the space age, sparked by the launch of Sputnik, won by the Soviet Union in 1957, fundamentally and irrevocably altered this reality. Suddenly, what was once pure fantasy became a tangible and fiercely contested national goal. But even with the advent of powerful rockets, directly observing the far side posed a unique and immediate new problem: communication. A spacecraft on the far side of the moon would be completely and totally blocked by the 2,159-mile of wide body of the moon itself from sending its radio signals directly back to Earth. It would be in a communication blind spot, a cosmic radio shadow. Any data it collected, any images it captured, would be trapped on board, lost to us forever, unless a clever solution could be found. This challenge necessitated the development of advanced, and at the time, highly speculative, relay technologies, such as orbiting satellites that could receive a signal from a far-side probe and then retransmit it back to Earth. Without such a relay, any long-duration mission to the far side would be an exercise in futility, a journey into a silent and dataless unknown. The first, historic and successful venture to pierce this veil of mystery was undertaken by the Soviet Union. In October of 1959, their Luna 3 probe, a small and, by modern standards, incredibly primitive spacecraft, swung around the moon, becoming the first human-made object to ever capture an image of this enigmatic and long-hidden territory. The images were crude, blurry, and distorted, the product of a primitive, on-board, film processing and scanning system, and a tenuous, long-distance radio link. But they were revolutionary. They were the first flickering and ghost-like glimpses of a new world, and they revealed a landscape that was immediately and strikingly different from the familiar face of the near side. The images showed a surface that was much more heavily and uniformly cratered, and was notably and almost completely lacking in the large, dark volcanic plains, the Maria, that so prominently define the visible lunar landscape. This initial, stunning revelation confirmed that the far side was not simply a mirror image of the near side. It possessed its own distinct geological character, a character that hinted at a different and perhaps more ancient evolutionary history. The excitement generated by these first distant photographs was immense, and it set the stage for a new era of lunar exploration. An era in which the once hidden far side of the moon would slowly and beautifully yield its long-held secrets to the relentless and insatiable curiosity of a new and spacefaring human species. The blurry images from Luna 3 were a tantalizing first step, but they were far from providing a comprehensive understanding. NASA, then a relatively young but ambitious space agency, quickly began its own parallel program of lunar exploration, a program that would culminate in the historic human landings of the Apollo missions. While these early NASA missions, for practical reasons of landing site selection and communication, were primarily focused on the near side, the scientific imperative to explore and to understand the entire moon, including its hidden far side, remained a powerful and enduring driving force. The journey to unveil the hidden moon was long and arduous, a journey that required decades of meticulous scientific planning, of breathtaking technological innovation, and of a fierce international competition that would ultimately push humanity beyond its terrestrial cradle and out into the vast and beautiful mystery of the cosmos. The human fascination with the moon, and with the heavens in general, is a story that is as old as our species itself. Before the advent of the scientific method, before the invention of the telescope, and long before the very concept of space travel had entered our collective imagination, the moon was a mystical and powerful object, a luminous silver orb in the night sky that inspired awe, wonder, and countless myths. Ancient civilizations across the globe wove elaborate and often beautiful tales around this celestial body, associating it with deities, with fertility, with the inexorable passage of time, and with the deep and often frightening mysteries of the night. It was seen as a silver chariot, driven by a goddess across the celestial vault, as a watchful and sometimes judgmental eye gazing down upon the affairs of mortals, or as a powerful and often capricious entity that influenced the tides, the harvests, and the very rhythms of life and death. These early pre-scientific inquiries were not about physical travel, but about finding meaning, about understanding the moon's nature and its spiritual significance in a universe that was, for the most part, a deep and terrifying unknown. But even in this age of myth, the seeds of a more scientific understanding were being sown. The ancient Greek philosopher Anaxagoras, in the 5th century before the Common Era, made the bold, and for his time, heretical suggestion that the moon was not a divine light source, but a rocky, Earth-like body, that its light was not its own, but was merely the reflected light of the sun. This was a radical and dangerous idea, one that challenged the prevailing mystical beliefs of his time, and one that laid a foundational, if rudimentary, stone for the great edifice of scientific inquiry that was to come. Aristotle, another towering figure of ancient Greek thought, built upon these early observational insights, integrating them into his comprehensive and for centuries dominant geocentric model of the universe, a model in which the Earth was the fixed and special center of all creation, and all the celestial bodies, including the moon, moved in perfect crystalline circles around it. While his model was ultimately and spectacularly wrong, his systematic and deeply empirical approach to observing and theorizing about the cosmos would influence Western thought for over 1,000 years. The idea of the moon as a world, a place of substance, a destination, began to take a tenuous but persistent root in these early philosophical inquiries. The dream of flight, of transcending our earthly bonds, also permeates the myths and legends of the ancient world. The story of Icarus, who fashioned wings of feathers and wax and attempted to fly to the sun, only to have his wings melt and to plunge to his death in the sea, is a powerful and enduring allegory for humanity's deep, and often tragic, aspiration to conquer the skies. While these were not direct dreams of space travel, they represented a fundamental and deeply human yearning to escape the confines of the Earth's surface, a necessary psychological precursor to the grander, and at the time, unimaginable, ambition of reaching other celestial bodies. For many centuries, the lack of a fundamental, scientific understanding of the basic principles of physics, of gravity, of the nature of the atmosphere, and the vacuum of space meant that the concept of traveling to the moon remained firmly and safely in the realm of fantasy and allegory. It was a subject for poets and storytellers, not for engineers and scientists. The 17th century, however, marked a pivotal and revolutionary shift. The invention of the telescope and its subsequent brilliant application to the heavens by Galileo Galilei fundamentally and irrevocably transformed our understanding of the universe. Galileo's telescopic observations in the early 1600s revealed that the moon was not the perfect, smooth, and ethereal sphere of Aristotelian philosophy, but a rugged and deeply familiar world, a world with mountains, with valleys, with vast dark plains, and with countless craters, a landscape that was, in many ways, strikingly similar to the landscapes of our own Earth. He even, with a beautiful and simple piece of geometric reasoning, estimated the heights of the lunar mountains by carefully observing the lengths of the shadows they cast. This new empirical evidence, derived from direct and repeatable observation, solidified the idea of the moon as a physical body, a world in its own right, a place that one could, in principle, visit. This new scientific understanding spurred a new wave of imaginative leaps, a shift from the realm of pure myth to a more grounded, albeit still fictional, exploration of the practicalities of lunar travel. In the mid-1600s, the French writer Cyrano de Bergerac, in his comical history of the states and empires of the moon, imagined a series of fantastical, but for the first time, vaguely mechanical, methods of reaching the moon, including using dew-filled bottles that would be drawn upwards by the morning sun, or a machine powered by a series of firecrackers, a primitive, but recognizable, rocket. Around the same time, the English bishop Francis Godwin, in his The Man in the Moon, described a protagonist who travels to the moon in a chariot pulled by a team of trained and exceptionally strong geese. These narratives, while charmingly unscientific, were significant. They represented a new and deeply modern human desire to imagine the mechanics of such a journey, to grapple, however imaginatively, with the practical challenges of space travel. The 19th century saw a flourishing of this new genre of speculative fiction, a genre that increasingly and skillfully intertwined the latest scientific concepts with bold, imaginative storytelling. The French novelist Jules Verne became a titan of this new form. His 1865 novel, From the Earth to the Moon, is perhaps the most famous and influential work of early space travel fiction. Verne's concept for lunar travel was a giant, spacefaring cannon, the Columbiad, which would fire a projectile containing 3 intrepid passengers directly towards the moon, while a cannon launch would, in reality, be instantly lethal to any human occupants due to the immense and crushing G-forces. Verne's attention to scientific detail was, for his time, remarkable. He consulted with scientists and engineers, and he meticulously, and for the most part, correctly, calculated the required muzzle velocity to escape the Earth's gravity, the trajectory of the projectile, and even the financial cost of such an immense undertaking. He described, with a surprising degree of accuracy, the experience of weightlessness in space and the challenges of life support in a sealed and very small capsule. His work captivated the public imagination and, in a subtle but powerful way, introduced the fundamental principles of ballistics, of orbital mechanics, and of the very possibility of space travel to a vast and hungry popular audience. Another great 19th century author, H.G. Wells, in his 1901 novel, The First Men in the Moon, conceived of a more scientifically imaginative and, in some ways, more prophetic method of propulsion, a substance he called cavorite, which had the magical property of nullifying gravity. While entirely fictional, this concept allowed Wells to explore the idea of a controlled and returnable flight to the moon, and to create a vivid and often terrifying portrayal of a complex and ancient alien civilization of insect-like selenites who lived in vast underground caverns. These literary works were crucial. They were a necessary imaginative bridge between the pure fantasy of the ancient myths and the burgeoning, hard-nosed, and practical fields of physics and engineering. They cultivated a widespread public fascination with space travel, transforming it from an obscure scientific concept into an exciting and seemingly plausible future human endeavor. They inspired generations of future scientists and engineers, the very people who would one day turn these fantastical dreams into a hard and beautiful reality. The true intellectual and scientific groundwork for space travel was laid by a small and remarkable group of visionary thinkers in the late 19th and early 20th centuries. These were the true fathers of rocketry, men who, often working independently and against considerable public and scientific ridicule, developed the fundamental theoretical principles of astronautics. The first, and in many ways the most important of these, was Konstantin Tsiolkovsky, a largely self-taught and profoundly deaf Russian school teacher, working in relative and often impoverished isolation in the late 1800s and early 1900s. Tsiolkovsky, with a stunning and almost preternatural clarity, laid out the entire theoretical blueprint for space travel. He famously and correctly formulated the rocket equation, a fundamental and elegant piece of mathematics that describes the change in velocity that a rocket can achieve based on the exhaust velocity of its propellant and the ratio of its initial fueled mass to its final empty mass. This equation revealed the two crucial keys to spaceflight: high exhaust velocities and a high mass ratio. Tsiolkovsky was a passionate and early advocate for liquid-fueled rockets, recognizing their superior efficiency and controllability compared to the simple, solid-fueled rockets of his time. He was the first to seriously conceptualize multi-stage rockets. The idea of shedding the dead weight of empty fuel tanks and engines during flight, a technique that is absolutely essential for achieving orbital and escape velocities. He even, with a remarkable foresight, theorized about the use of liquid oxygen and liquid hydrogen as propellants, a combination that, due to its exceptional energy density, is still used in many of our most powerful modern rockets today. But Tsiolkovsky was more than just a brilliant technical theorist. He was a deep, and in some ways, mystical, philosophical thinker. He envisioned a future for humanity that lay not on Earth, but in space. He dreamed of space stations, of lunar bases, of the colonization of the solar system, and of an ultimate human destiny among the stars. His work, though largely unknown outside of Russia during his lifetime, provided the complete and uncannily accurate theoretical foundation upon which all subsequent practical developments in rocketry would be built. Across the Atlantic, in the United States, another, and very different, kind of pioneer was at work. Robert Goddard, an American physicist, was not primarily a theorist, but a tireless and often frustrated, hands-on experimenter. He was often ridiculed by the press, who famously and wrongly asserted in a New York Times editorial that a rocket could not work in the vacuum of space because it would have nothing to push against. But Goddard, undeterred, persisted, and in 1926, on a cold March day in a field in Auburn, Massachusetts, he achieved a monumental and historic feat, the launch of the world's first liquid-fueled rocket. The rocket, which he had nicknamed Nell, was a small and rather unimpressive-looking contraption. It flew for only 2.5 seconds and reached an altitude of only 41 feet, but it was a transformative moment. It was the Kitty Hawk of rocketry, the first tangible proof that the theoretical promise of liquid-fueled rockets could be turned into a working physical reality. Goddard continued to develop and test more powerful and sophisticated rockets throughout his career, often facing funding challenges and working with very limited resources. He was a prolific inventor, and he held patents for many of the key components of a modern rocket, including multi-stage designs, fuel pumps, and gyroscopic guidance systems. He was the man who solved, through painstaking and often dangerous trial and error, many of the practical engineering problems that Tsiolkovsky had only dreamed about. And in Germany, another key figure, Hermann Oberth, was independently exploring the theoretical possibilities of spaceflight. His 1923 book, The Rocket into Interplanetary Space, was a rigorous mathematical exploration of the principles of rocket propulsion, and it had a profound influence on a generation of German rocket enthusiasts, including a young and ambitious engineer named Wernher von Braun. Together, Tsiolkovsky, Goddard, and Oberth are rightly known as the fathers of modern rocketry. Their independent, but remarkably convergent work formed the solid theoretical and practical bedrock of astronautics. They were the ones who showed that escape velocity, the speed required to break free from a planet's gravitational pull, was not an impossible dream, but a solvable, if difficult, engineering challenge. The grim and terrible reality of the Second World War inadvertently and tragically accelerated this development. The German V-2 rocket, developed under the leadership of Wernher von Braun, was a weapon of terror, but it was also the world's first large-scale, liquid-fueled, ballistic missile, a machine that was capable of reaching the very edge of space. After the war, both the United States and the Soviet Union scrambled to capture the German rocket scientists and their advanced V-2 technology, a process that provided a significant and morally complex leap forward for their own nascent missile and space programs. The dawn of the Cold War, in the mid-20th century, then provided the final, powerful geopolitical impetus for the race to space. The launch of Sputnik, won by the Soviet Union in October of 1957, was a profound, and for many in the West, terrifying shock. It was a clear and unambiguous demonstration of Soviet technological prowess, and it ignited a fierce and desperate determination in the United States to catch up and to surpass their ideological rivals. This event led directly to the creation of the National Aeronautics and Space Administration, NASA, in 1958, a new civilian agency that would consolidate and lead America's efforts in space. The race to the moon was on, and the once fantastical dreams of the early visionary thinkers were about to become a monumental national endeavor, an endeavor that would, in the short span of a single decade, take humanity from its first Tentative steps into orbit to its first giant leap onto the surface of another world. For untold millennia, the far side of the moon remained an impenetrable mystery to humanity. From our terrestrial vantage point, only one familiar face of our celestial neighbor was ever visible, a beautiful and frustrating consequence of the gravitational dance known as tidal locking. This meant that any true knowledge of the moon's other hidden hemisphere would require a monumental leap in our technological capabilities, a leap that would take us beyond the Earth's atmosphere and into the vast, dark expanse of cislunar space. The mid-20th century witnessed the beginning of this transformative era, as the burgeoning space race between the United States and the Soviet Union propelled humanity towards its first direct observations of this enigmatic lunar territory. And it was the Soviet Union, with its early and impressive lead in powerful long-range rocket technology, that would achieve this pioneering feat, providing the world with its first blurry, but profoundly significant, glimpses of the moon's unseen side. The mission that was responsible for this groundbreaking achievement was Luna 3, a small, and by today's standards, incredibly primitive robotic probe. Its launch, in October of 1959, came just 2 years after the momentous, and for the West, deeply shocking, launch of Sputnik 1, the world's first artificial satellite. The Luna 3 mission was audacious for its time. It was designed not just to orbit the Earth, but to journey 250,000 miles to the moon, to swing around it in a complex gravitational ballet, and then, if all went well, to transmit its precious photographic cargo back across the vast and empty gulf of space. Its primary objective was singular, historic, and revolutionary: to photograph the side of the moon that had never before been seen by a human eye, or indeed, by any terrestrial instrument. The design of the Luna 3 spacecraft was a marvel of late 1950s engineering, a testament to the ingenuity of the Soviet space program, but also a reflection of the severe technological constraints of the era. It was a cylindrical craft, equipped with solar panels for power and a set of simple, whip-like antennas for communication. Its most crucial and most ingenious component was its imaging system. This was not a digital camera, which had not yet been invented. It was a complex and delicate system of 2 film-based cameras, a small, onboard, automated film processing laboratory, and a miniature, television-like scanning device. The system was designed to capture a series of images on traditional photographic film. Then, in the harsh and unforgiving vacuum of space, the film would be automatically developed, fixed, and dried. Once the images were processed, a tiny flying light spot would scan the developed film, line by line, converting the variations in light and shadow into an analog, electrical signal. This signal was then transmitted, slowly and painstakingly, back to the massive radio dishes of the deep space network on Earth. This method was inherently prone to noise, to distortion, to the 1,001 things that can go wrong in a complex, automated system operating hundreds of thousands of miles from home. But it was the cutting edge of remote imaging technology for its time. The trajectory of Luna 3 was another masterpiece of early celestial navigation. It was not designed to enter a stable orbit around the moon, but to perform a circumlunar flyby. It was launched from Earth on a direct translunar trajectory. It then used the moon's own gravity to bend its path, to swing it around the far side, and then to fling it back towards the Earth on a long, looping, and highly elliptical orbit. This gravity assist maneuver was a clever and efficient way to achieve the desired path without the need for a large and heavy onboard rocket engine for course correction. The timing of the photographic sequence was critical. The spacecraft had to be in the right place at the right time, with the sun in the right position to illuminate the far side. On October 7, 1959, as Luna 3 gracefully arced around the far side of the moon. Its cameras clicked and whirred, capturing 29 images of the previously unseen hemisphere. The images, once they were finally received and processed on Earth, were, by modern standards, of a shockingly poor quality. They were blurry. They were low resolution. They were streaked with static and marred by transmission artifacts. But they were, without a doubt, one of the most important and most breathtaking set of images ever taken. They were the first empirical evidence of what lay on the other side of our own moon. And what they revealed was a landscape that was immediately and strikingly different. The familiar near side of the moon is defined by its extensive, dark, and relatively smooth plains, the Maria. But the Luna 3 images showed a far side that was almost completely devoid of these large, dark features. Instead, it was a continuous and seemingly endless expanse of bright, rugged, and heavily cratered terrain. This was not just a minor cosmetic difference. It was a profound geological dichotomy. It suggested that the two hemispheres of the moon had experienced vastly different evolutionary histories. The far side appeared to be an older, more ancient, and more heavily battered surface, a surface that had not been subject to the same large-scale volcanic resurfacing that had shaped the near side. This single, stunning observation sparked a revolution in lunar science. It forced a complete re-evaluation of our models of the moon's formation, of its internal structure, and of its thermal history. The simple and long-held assumption of a uniform, symmetric moon was shattered forever. The naming of the newly discovered features on the far side also began with these first blurry images. The Soviet scientists, in a move that reflected the national pride of their achievement, named one of the few, small, dark patches they could discern Mare Moscoviense, the Sea of Moscow. A prominent crater was named after their great visionary rocket pioneer, Konstantin Tsiolkovsky. These names were the first human brushstrokes on a canvas that had been, for all of history, completely blank. The impact of Luna 3's achievement was immense. It was a massive propaganda victory for the Soviet Union in the intense, and often bitter, Cold War space race. It was a moment of deep and almost universal awe for the public around the world, a moment that transformed the moon from a distant, mystical object into a real, tangible, and now partially known world. And for the scientific community, it was a tantalizing and deeply provocative first glimpse into a new and unknown land, a glimpse that would ignite a decades-long and still ongoing quest to fully understand the profound and beautiful asymmetry of our own celestial companion, Celestial. The launch of Sputnik 1 in 1957 was a profound, and for many in the United States, a deeply unsettling wake-up call. The small, beeping satellite, circling the Earth every 96 minutes, was a clear and unambiguous demonstration of Soviet technological prowess, and it ignited a fierce, and often frantic, sense of urgency in the American government and public. Before Sputnik, American efforts in space were fragmented, a patchwork of competing and often uncoordinated programs within the different branches of the military, and a smaller civilian research effort led by the National Advisory Committee for Aeronautics, or NACA. The Sputnik crisis made it abundantly and painfully clear that a new, more unified, and more ambitious approach was needed. In July of 1958, President Dwight D. Eisenhower signed the National Aeronautics and Space Act into law, creating a new, powerful, and civilian-led agency, NASA. The new agency absorbed the old NACA, along with its skilled engineers and its world-class research facilities, and it was given a clear and audacious mandate to lead America's efforts in the peaceful exploration of space. The initial goal was simply to catch up to the Soviets, but this soon evolved into a much grander and more ambitious vision, a vision that would be articulated with a powerful and enduring rhetoric by a new, young president. In 1961, President John F. Kennedy, in a speech before a joint session of Congress, threw down the ultimate cosmic gauntlet. He challenged the nation to commit itself to achieving the goal, before the decade was out, of landing a man on the moon and returning him safely to the Earth. This was not just a scientific goal, it was a political and deeply symbolic. 1. It was a declaration of national will, a bold and risky gambit in the high-stakes, ideological battle of the Cold War. And it was a challenge that would galvanize the nation and set NASA on a course that would lead to one of the greatest and most inspiring adventures in all of human history. But before humans could take their first giant leap, a vast amount of groundwork had to be laid. The moon was still, in many ways, an unknown and dangerous world. We needed to know what its surface was like, whether it was solid enough to support a lander, what dangers it might hold. And so, before the Apollo astronauts could fly, their robotic scouts had to go first. The Ranger program was NASA's first, and often frustrating, attempt to get a close-up look at the lunar surface. The plan was simple, if brutal, to send a series of probes on a direct collision course with the moon, transmitting high-resolution television images back to Earth in the final, frantic minutes before their impact. The early Ranger missions were a string of heartbreaking failures, a testament to the immense, and often unforgiving, difficulty of early, deep space exploration. But with Ranger 7, in July of 1964, NASA finally succeeded. The probe transmitted over 4,300 close-up images, revealing the lunar terrain in unprecedented detail, and confirming that the surface was, indeed, solid enough to land on. Following the success of the Ranger impactors, NASA embarked on the much more complex and much more ambitious Surveyor program. The goal of Surveyor was not to crash, but to land, to achieve the first, controlled, soft landing on the lunar surface. Each Surveyor spacecraft was a marvel of 1960s engineering, an insect-like contraption equipped with a powerful, solid-fuel retro rocket to slow its descent, and a set of smaller, liquid-fueled Vernier engines for fine-tuned terminal guidance. In June of 1966, Surveyor 1 made a perfect, gentle touchdown on the ocean of storms, a stunning and deeply emotional success for the young space agency. It transmitted over 11,000 images of its surroundings, showing a landscape of fine-grained, sandy material littered with small rocks and pebbles. Later, Surveyor missions carried more sophisticated instruments, including a robotic arm with a scoop that could dig into the lunar soil, and an alpha scattering device that could perform a direct chemical analysis of the lunar regolith. The Surveyor program was the ultimate and successful dress rehearsal for the Apollo landings. It proved that we could land safely, and it gave us our first direct and tangible knowledge of the strange, new ground upon which our astronauts would one day walk. At the same time, the Lunar Orbiter program was systematically mapping the entire moon from orbit, including both the near and the far sides, with a series of 5 highly successful photographic missions. The primary goal was to scout and to certify the safest and most scientifically interesting potential landing sites for the Apollo missions. The orbiters produced a comprehensive and beautiful photographic atlas of the moon, a set of images that not only served a crucial practical purpose, but also revealed, in stunning, high-resolution detail, the full, rugged, and ancient beauty of the lunar landscape. Together, the Ranger Surveyor, And lunar orbiter programs were the necessary, robotic precursors to the human adventure that was to come. They were the eyes, the ears, and the hands that we sent ahead, the silent and often heroic. Scouts that paved the way for the first human steps onto another world. The Apollo program was not just a technological achievement. It was a human drama of immense proportions, a story of courage, of ingenuity, of sacrifice, and of profound, and often unexpected, discovery. And it was the astronauts of the Apollo missions who would become the first, and so far, only, human beings to ever see, with their own eyes, the hidden, far side of the moon. The first of these historic journeys was Apollo 8, in December of 1968. In a bold, and at the time, deeply risky decision, NASA sent the crew of Frank Borman, James Lovell, and William Anders on a direct circumlunar flight, the first time that human beings had ever left the gravitational embrace of the Earth and traveled to another celestial body. As their spacecraft rounded the limb of the moon, and the Earth, for the first time in human history, disappeared from view, they were greeted by a landscape that was both awe-inspiring and deeply unsettling. "It's a vast, lonely, forbidding expanse of nothing," one of the astronauts reported back to a transfixed world. "It looks like plaster of Paris." Their live television broadcasts, though grainy and in black and white, gave humanity its first shared human experience of another world. And it was on this mission, as they came around from the far side for the fourth time, that William Anders took one of the most iconic and most influential photographs in all of human history, Earthrise. The image of our own small, fragile, and beautiful blue planet rising above the stark, gray, and lifeless horizon of the moon was a profound, and for many, a deeply spiritual moment. It was a picture that, in a single, silent frame, captured the beauty of our own world, the desolation of the moon, and the profound and inescapable truth of our own cosmic isolation. The missions that followed, from Apollo 10's full dress rehearsal to Apollo 17's final triumphant landing, all involved multiple orbits around the moon. And with each orbit, the astronauts were given a new and often different view of the far side. The command module pilots, who remained in orbit while their crewmates descended to the surface, Michael Collins on Apollo 11, Richard Gordon on Apollo 12, Stuart Roosa on Apollo 14, Al Worden on Apollo 15, Ken Mattingly on Apollo 16, and Ron Evans on Apollo 17 all experienced a unique and profound form of solitude. For long periods of time, they were the most isolated human beings in the history of the universe, alone in their tiny spacecraft, circling a dead world, their only connection to the 7 billion other souls of their species. A fragile radio link that was, for 20 minutes of every 2-hour orbit, completely and totally silent. As they passed behind the moon into the radio shadow, they were truly and completely on their own. And in these moments of profound and beautiful isolation, they were the only human beings to ever see the full sunlit expanse of the far side. Their descriptions, in their mission logs and their later memoirs, are a testament to the power and the poetry of human exploration. They spoke of its stark and almost brutal beauty, of its endless and seemingly uniform sea of craters, of its profound and almost terrifying sense of ancientness. It was a world that had not been softened by the gentle hand of erosion, a world that wore the scars of its violent 4-billion-year-long history on its face. It was a world, they all agreed, that was not like home, Even the ill-fated Apollo 13 mission, a mission that was a near disaster, provided a dramatic and unintentional human encounter with the far side. After an explosion crippled their spacecraft on the way to the moon, the crew was forced to use the moon's gravity to swing them around on a free return trajectory back to Earth. For the distressed crew of James Lovell, Jack Swigert, and Fred Hayes, the long, silent pass behind the far side was a moment of immense and almost unbearable tension, a period of radio silence when they were at their most vulnerable, their most isolated, and their most uncertain of their own survival. Their experience, though not one of scientific observation, was a powerful and deeply human testament to the isolating and unforgiving nature of this hidden lunar hemisphere. The cumulative human observations from all the Apollo missions, when combined with the precise and systematic data from the robotic probes, gave us a new and much richer understanding of the moon. They confirmed, in a direct and visceral way, the profound geological asymmetry between the two hemispheres, and they gave us a new and more profound sense of our own small and precious place in the vast and often hostile cosmos. The surface of the moon is a museum of cosmic violence, a gallery of scars that tells the long and tumultuous story of the early solar system. And the largest, oldest, and most magnificent exhibit in this museum is the South Pole Aitken Basin, a colossal impact structure on the lunar far side that is one of the largest and oldest known impact features in our entire solar system. The basin was not discovered in a single eureka moment, but was gradually and painstakingly revealed through a series of robotic missions that have, over the decades, peeled back the layers of its mystery. The first, faint hints of its existence came from the blurry 1959 images from the Soviet Luna 3 probe. But it was NASA's Lunar Orbiter and Apollo missions in the 1960s that provided the first high-resolution photographic evidence of the vast and subtle depression that marks its location. And it has been the more recent and more sophisticated missions of the late 20th and early 21st centuries that have truly brought this ancient and monumental feature into sharp focus. The basin gets its name from its location. It is centered near the lunar South Pole, and its northern rim is marked by the smaller, but still prominent, Aitken crater. Its dimensions are staggering. It is approximately 2,500 kilometers, or 1,550 miles, in diameter, a distance that would stretch from New York City to Dallas. And it is incredibly deep, ranging from 8 to 13 kilometers, or 5 to 8 miles, from its highest mountainous rim to its lowest cratered floor. It is an impact scar of truly planetary proportions, and it is ancient. Scientists estimate that the impact that created the South Pole Aitken Basin, or SPA, occurred very early in the Moon's history, sometime between 4.3 and 4.2 billion years ago. This places its formation squarely within the late heavy bombardment, a hypothesized and still not fully understood period in the early solar system when the inner planets and their moons were subjected to an intense and prolonged fusillade of asteroids and comets. The SPA basin is, in a sense, the Moon's oldest and deepest wound. The impact that created it must have been an event of almost unimaginable violence. The prevailing theory is that it was formed by the collision of a massive asteroid or comet, perhaps several hundred kilometers in diameter, traveling at a speed of tens of thousands of miles per hour. The energy released in this cataclysmic event would have been far, far greater than all of the nuclear weapons on Earth combined. It would have instantaneously vaporized, melted, and ejected a colossal amount of the Moon's primordial crust, sending a shockwave of seismic energy reverberating through the entire lunar body. The most profound and scientifically significant. Consequence of this impact is that it is thought to have punched a hole clear through the moon's crust and to have excavated material from the deep underlying mantle. This is a discovery of immense importance, as it offers us a rare and precious natural window into the deep interior of the moon. NASA's missions have been paramount in confirming this mantle excavation hypothesis. In the 1990s, the Galileo and Clementine spacecraft, with their multispectral imagers, provided the first tantalizing hints that the floor of the SPA basin had a different and unusual mineral composition. Then, in 1998, the Lunar Prospector mission, with its gamma-ray spectrometer, created the first global maps of the moon's elemental composition. These maps revealed a striking anomaly. The floor of the SPA basin has a significantly higher concentration of iron and titanium than the surrounding highland crust. These are elements that are thought to be more abundant in the denser mantle material, but the most comprehensive and most definitive. Data has come from the Lunar Reconnaissance Orbiter, or LRO, which has been orbiting the moon since 2009. LRO's suite of advanced instruments has given us an unprecedented and multifaceted view of the SPA basin. Its laser altimeter has created a precise, three-dimensional topographic map, revealing the basin's true depth and its complex, multi-ring structure. Its radiometer has mapped the thermal properties of the surface, providing further clues to its mineral composition. And its high-resolution cameras have given us stunning, detailed images of the terrain within the basin. When all of this data is combined, a clear and consistent picture emerges. The floor of the South Pole Aitken Basin is a unique geological province, a place where the deep and normally hidden interior of the moon has been brought up to the surface. It is a natural laboratory for studying the composition of the lunar mantle, a study that is crucial for understanding the moon's overall formation, its thermal history, and its differentiation into a layered planetary body. This is a gift of almost incalculable scientific value. It gives us a way to sample the deep interior of another world without the immense, and at present, impossible, technological challenge of having to drill tens of kilometers through its solid, rocky crust. The SPA Basin is also a place of great interest for future exploration. It encompasses the lunar South Pole, a region where, in the deep and permanent shadows of certain craters, LRO and other missions have confirmed the existence of significant deposits of water ice. This discovery has transformed our view of the moon from a bone-dry, barren world into a place with a potentially valuable and life-sustaining resource. This water ice, if it can be mined and processed, could provide drinking water, breathable oxygen, and rocket propellant for future human lunar outposts. The South Pole Aitken Basin, with its unique, ancient geology, its window into the lunar mantle, and its proximity to these precious polar ice deposits, is, without a doubt, one of the most scientifically compelling and strategically important locations in our entire solar system. It is a place where the deep past and the potential future of lunar exploration come together in a single, magnificent, and awe-inspiring landscape. And in 2019, humanity, through the Chinese Chang'e 4 mission, took its first, historic, robotic step into this new and exciting world, a world that was, for so long, hidden from our view. The surface of the moon is a history book written in the language of craters, unlike the Earth, with its dynamic atmosphere, its flowing water, and its active plate tectonic geology. The moon is a world of profound and beautiful stasis. It has no wind, no rain, no rivers to erode its surface. Its geological engine cooled and died billions of years ago. And so, the scars of its violent past, the countless impact craters that have pockmarked its surface over the eons, have been preserved with an almost perfect and often breathtaking clarity. But this history book is not a uniform one. One of the most striking and most fundamental. Discoveries of the space age has been the profound and deeply mysterious asymmetry between the moon's near side and its far side. The near side, the face that is forever turned towards the Earth, is a world of two distinct terrains, the bright, ancient, and heavily cratered highlands, and the dark, younger, and relatively smooth Maria. The far side, on the other hand, is an almost continuous and seemingly endless expanse of heavily cratered highlands, the great dark Maria. The seas of solidified lava that so prominently define the near side are almost completely absent. This stark dichotomy in the density of craters and in the extent of volcanic resurfacing is one of the central puzzles of lunar science and NASA's missions. From the first, robotic scouts to the human explorers of the Apollo program have been instrumental in piecing together the clues that are now allowing us to solve it. The answer to this puzzle lies deep within the moon's own, hidden interior. The key is the thickness of the lunar crust. Our detailed global maps of the moon's gravity field, most notably from the Grail mission, have revealed that the crust on the far side is significantly and systematically thicker than the crust on the near side. On average, the far side crust is about 60 kilometers thick, while the near side crust is only about 30 kilometers thick. This is a profound and fundamental asymmetry, and it is thought to be a relic of the moon's very formation. In the aftermath of the giant impact that created the moon, as the debris coalesced and the moon cooled from a molten state, the Earth's immense gravitational pull and the uneven distribution of heat-producing radioactive elements may have led to this lopsided crustal structure. And this difference in crustal thickness has had a dramatic and lasting impact on the moon's geological evolution. The Maria were formed by vast outpourings of basaltic lava from the moon's deep, and at the time, still molten, mantle. On the near side, the thinner crust provided an easier path for this magma to reach the surface. The immense impacts that created the great near-side basins also created deep fractures in this thinner crust, providing ready-made conduits for the upwelling lava. The result was a series of massive volcanic flood events that filled these basins and buried the older, cratered terrain beneath them. On the far side, however, the much thicker crust acted as a formidable barrier. Even when giant impacts created vast basins, the magma from the mantle simply could not, for the most part, find its way to the surface. The far side, therefore, was largely spared from this volcanic resurfacing. Its ancient cratered highlands, the primordial crust of the moon, were preserved. It is a more pristine, and in many ways, a more honest record of the early violent history of the solar system. This story is further supported by another, subtle, but crucial, discovery. The Lunar Prospector mission, with its gamma-ray spectrometer, found that the heat-producing radioactive elements of potassium, uranium, and thorium are not uniformly distributed throughout the moon. They are concentrated in a vast geological province on the near side, a region known as the Procellarum Creep Terrain. This region, with its higher concentration of internal heat sources, would have remained hotter and more volcanically active for longer, further contributing to the extensive mare-forming volcanism on the near side. The far side, being relatively depleted in these elements, would have cooled more quickly, its volcanic engine sputtering and dying out much earlier in its history. The implications of this cratered asymmetry are profound. It means that the far side of the moon is, in a very real sense, a different world. It is an older world, a more ancient world, a world that has preserved a more complete and more pristine record of the late heavy bombardment. That intense and chaotic period in the early solar system when the inner planets were subjected to a relentless fusillade of asteroids and comets. By studying the number, the size, and the distribution of the craters on the far side, and by comparing them with the ages of the rocks brought back by the Apollo astronauts from the near side, We can reconstruct the history of this bombardment with a remarkable degree of precision. This is a technique known as crater counting, and the Moon, with its two distinct and beautifully preserved faces, is our primary and most valuable Rosetta Stone for deciphering the ancient and violent history of our entire solar system. The far side is not just the other side of the Moon, it is a window into the deep past, a silent and beautiful testament to the fiery and creative chaos of our own cosmic origins. The lunar highlands, the bright, rugged, and ancient terrains that dominate the far side of the Moon, are the oldest and, in many ways, the most important landscapes on our celestial neighbor. They are the primordial crust of the Moon, a fossilized record of its fiery birth and its turbulent youth. And they hold the key to understanding not just the history of the Moon, but the very process of planetary formation itself. The prevailing theory for the origin of the highlands is the lunar magma ocean hypothesis. This theory proposes that shortly after its formation, some 4.5 billion years ago, the Moon was a global molten sphere, a vast incandescent ocean of rock. As this magma ocean slowly cooled and solidified, a process of differentiation occurred. Denser minerals, rich in iron and magnesium, crystallized and sank towards the center, forming the Moon's mantle and its small metallic core. Lighter minerals, however, particularly a type of feldspar known as plagioclase, crystallized and floated to the surface like a layer of creamy slag on a molten metal. Over millions of years, this buoyant, plagioclase-rich material accumulated and solidified to form a thick, global crust of a light-colored, low-density rock called anorthosite. This primordial, anorthositic crust is what we now see as the lunar highlands. This theory, which was first proposed in the 1970s, was a bold and brilliant piece of scientific inference, and it has been confirmed with a stunning degree of precision by the samples brought back from the Moon by the Apollo astronauts. The rocks collected from the highland regions on the near side were, indeed, predominantly anorthosites, their great age confirming their primordial origin. The highlands are a landscape of almost unimaginable antiquity, a surface that has been preserved, largely unchanged, for over 4 billion years. And they are a landscape of almost unimaginable violence. They are saturated with impact craters, the result of a relentless and seemingly endless bombardment by asteroids and comets in the early, chaotic history of the solar system. The surface of the highlands is not made of pristine, solid bedrock. It is a deep and thoroughly pulverized layer of regolith, a mixture of fine dust, broken rock fragments, and small, glassy beads that have been formed by the immense heat and pressure of countless impacts. And beneath this regolith lies a thick layer of breccia, a type of rock that is itself composed of the angular, cemented together fragments of older, shattered rocks. The highlands are a landscape that has been broken and rebroken again, a testament to a history of violence that is almost beyond our comprehension. And yet, it is precisely this violent history that makes the highlands so scientifically valuable. They are a pristine and beautifully preserved record of the late heavy bombardment. By studying the craters of the highlands, we can learn about the size, the number, and the nature of the objects that were careening through the early solar system. This is information that is crucial for understanding how the planets themselves formed, and how our own home world, the Earth, survived this early and very dangerous period of its life. The Earth, too, must have been subjected to this same intense bombardment, but on our dynamic and geologically active planet. The evidence of this ancient history has been almost completely erased, wiped clean by the relentless processes of plate tectonics, of volcanism, of erosion. The Moon, in its beautiful and silent stasis, has preserved the story that the Earth has forgotten. It is our celestial attic, our planetary memory, a place where the deep and often violent secrets of our own cosmic family are stored, the persistent and deeply ingrained. Popular misconception of a dark side of the moon is a beautiful example of how a simple linguistic ambiguity can lead to a profound and enduring scientific misunderstanding. The term dark side has a powerful and almost mystical resonance. It conjures up images of a perpetually shadowed and mysterious hemisphere, a realm of eternal night. But the reality is far more mundane, and in many ways, far more interesting. The moon does not have a dark side, it has a far side. And the far side is not perpetually dark. It experiences a regular and predictable cycle of day and night, just like the near side, and just like our own Earth. The confusion arises from the phenomenon of tidal locking, because the moon's rotation is synchronized with its orbit. The same hemisphere, the near side, is always facing the Earth. The other hemisphere, the far side, is therefore always facing away from us. It is dark in the old-fashioned sense of being unknown, of being hidden from our view. But it is not dark in the sense of being unlit. The source of light in our solar system is the sun, not the Earth. And as the moon orbits the Earth, it is also, of course, orbiting the sun over the course of a single lunar day. A period of about 29.5 Earth days, the sun's light sweeps across the entire spherical surface of the moon. Every part of the moon, both the near side and the far side, experiences about 2 weeks of continuous, brilliant daylight, followed by 2 weeks of deep, cold, and continuous night. The phases of the moon, as seen from Earth, are a direct consequence of this changing illumination. When we see a new moon, the moon is positioned between the Earth and the sun. The side of the moon that is facing us, the near side, is in darkness. But at that very same moment, the far side of the moon is fully illuminated, basking in the light of its own. High noon. Conversely, when we see a full moon, the Earth is positioned between the sun and the moon. The near side is fully illuminated, and at that moment, the far side is in the midst of its long, 2-week-long night. The first, definitive, and human confirmation of this simple but profound astronomical fact came with the Apollo 8 mission in December of 1968. As the astronauts became the first human beings to ever orbit the moon, their television camera, broadcasting back to a transfixed world, showed them the sunlit and deeply cratered landscape of the far side, and the iconic Earthrise photograph, taken on that same mission, is a beautiful and powerful testament to this reality. The image shows our own blue and white planet, rising above a stark, gray, and clearly sun-drenched lunar horizon. The landscape in the foreground of that photograph is on the far side of the moon. The only places on the moon that are truly perpetually dark are the deep and frigid floors of certain craters at the lunar poles, because of the moon's very small axial tilt. The sun is always very low on the horizon at the poles. This means that the floors of some deep craters are forever shielded from the direct rays of the sun. These permanently shadowed regions are some of the coldest places in our entire solar system. And it is in these cold, dark traps that the moon has been hiding its most precious and most surprising secret. For most of the 20th century, the scientific consensus was that the moon was a bone-dry and completely waterless world. The rock samples brought back by the Apollo astronauts, when first analyzed, seemed to confirm this view. They were found to be almost completely devoid of water. This dry moon paradigm had a profound and chilling effect on our plans for future human exploration. It meant that any long-term human presence on the moon would be an immense and costly logistical challenge, requiring all the necessary water for drinking, for life support, and for growing food to be ferried, at great expense, from the deep, gravitational well of the Earth. But in the last few decades, this paradigm has been completely and beautifully overturned. A series of sophisticated robotic missions, many of them led by NASA, has revealed that the moon is not as dry as we once thought. In the deep, dark, and permanently shadowed craters at its poles, it is hoarding a vast and potentially invaluable reservoir of water ice. The first tantalizing hints came in the 1990s from the Clementine and Lunar Prospector missions. These orbital probes, using radar and a neutron spectrometer, detected the telltale signatures of hydrogen concentrated in the polar regions. The most plausible form for this hydrogen, in these incredibly cold, permanently shadowed environments, was water ice. But the definitive, smoking gun proof came in 2009 with NASA's spectacular and deliberately destructive L-Cross mission. The mission involved intentionally crashing a spent Centaur rocket stage into a permanently shadowed crater at the moon's south pole. A second shepherding spacecraft then flew through the plume of debris that was kicked up by the impact, analyzing its composition with a suite of onboard instruments. The data was unambiguous. The spectrometers on the shepherding spacecraft detected the clear and unmistakable spectral signatures of both water vapor and water ice. The water was real. The discovery of water on the moon is a true game changer. Water is the single most important resource for supporting a long-term human presence in space. It can be used for drinking and for growing food. It can be split through electrolysis into its constituent elements, hydrogen and oxygen. The oxygen can be used for breathable air, and the hydrogen and oxygen, when recombined, are a powerful and clean rocket propellant. The moon, it turns out, has its own built-in gas station. The ability to mine and to utilize this lunar water, a process known as in situ resource utilization, or ISRU, is the key to creating a sustainable and ultimately a self-sufficient human presence on the moon. It is the key to breaking our complete and costly reliance on the Earth for all of our resources. It is the key that will unlock the door to a future where the moon is not just a place we visit, but a place where we live, and a place from which we can journey onwards to Mars and beyond. The discovery of water on the moon has transformed our nearest celestial neighbor from a barren geological museum into a dynamic and strategically important new frontier. A frontier that is rich with both scientific mystery and profound human possibility. The moon's gravitational field is not the smooth, uniformed, and perfectly spherical field of a textbook problem. It is a lumpy and complex gravitational landscape, a landscape of subtle hills and valleys that is a direct reflection of the uneven distribution of mass within the moon's interior. These gravity anomalies were first discovered serendipitously in the 1960s, when the mission controllers for NASA's Lunar Orbiter and Apollo missions noticed that their spacecraft were being mysteriously and frustratingly tugged off course as they orbited the moon. These unexpected orbital perturbations were caused by localized regions of unusually strong gravitational pull, regions that were quickly and evocatively dubbed mascons, for mass concentrations. The most prominent of these mascons were found to be associated with the large, circular, mare basins on the near side. This was a deep, and at the time, completely unexpected puzzle. These basins are the lowest points on the lunar surface. Why should they be the location of a large, excess mass? The answer, we now know, lies in a combination of two effects. The immense impacts that created these basins not only excavated a huge amount of the low-density crustal material, but they also caused the denser underlying mantle material to rebound upwards, closer to the surface. And then, these thinned-out basins were filled with a thick and very dense layer of basaltic lava. It is this combination of a raised, dense mantle and a thick, dense lava fill that creates the strong, positive gravity anomaly of the mascons. The fact that these mascons are still there, that they have not been erased by the slow, isostatic adjustment of the lunar crust over billions of years, tells us something profound about the moon's interior. It tells us that the moon's outer, solid layer, its lithosphere, has been very thick and very rigid for a very long time. It cooled and solidified much more quickly than the Earth's, and it has been for most of its history, a geologically dead and unyielding world. The far side, with its almost complete lack of large maria, also, unsurprisingly, lacks these large, prominent mascons. Even the colossal South Pole Aitken Basin does not have a strong, positive mascon. Its gravity signature is more subtle and more complex, a reflection of its different and more ancient history. But the most detailed and most beautiful map of the moon's gravity field has come from NASA's Grail mission. In 2011, two identical spacecraft, named, charmingly, Ebb and Flow, were placed in a close, tandem orbit around the moon by precisely and continuously measuring the tiny changes in the distance between the two spacecraft as they orbited, to an accuracy of a few microns. The mission was able to create an incredibly high-resolution map of the entire lunar gravity field. The map is a work of scientific art. It reveals not just the large mascons, but a wealth of smaller and more subtle anomalies associated with individual craters, with buried volcanic structures, and with the deep tectonic faults of the lunar crust. It is a new and powerful way of seeing the moon, an X-ray vision that allows us to peer beneath the surface and to map the hidden and complex architecture of its interior. The moon today does not have a global magnetic field. It lacks the hot convecting and electrically conducting liquid outer core that is required to generate a planetary dynamo, the kind that creates the Earth's protective magnetosphere. And yet, the moon is not entirely non-magnetic. The rock samples brought back by the Apollo astronauts were found to be surprisingly and mysteriously magnetic. And our orbital probes have detected a series of weak, localized, and patchy magnetic anomalies embedded in the lunar crust. These are fossil magnetic fields, the frozen and ghostly remnants of a time long ago when the moon was a very different and much more dynamic world. The existence of these remnant magnetic fields is a profound and beautiful clue. It tells us that in its distant past, for a period of at least 1 billion years, the moon did have a global magnetic field. It did have a hot, molten, and convecting core. It did have a dynamo. This discovery has revolutionized our understanding of the moon's thermal history, showing us that it was not a simple, cold, and inert body, but a true, and for a time, a geologically active planet. The distribution of these fossil magnetic fields is also deeply strange. They are much stronger and much more prevalent on the far side of the moon than on the near side. And some of the strongest of these far side anomalies are found in a very peculiar and very specific location at the antipode, the point on the moon's surface that is diametrically opposite to the large, young, and near-side impact basins, like Mare Imbrium. This is a stunning and deeply suggestive correlation, and it has led to a beautiful and compelling theory. The idea is that the immense energetic impacts the UAT created these near-side basins sent a powerful and highly focused seismic shockwave reverberating through the entire, and at the time, still molten, body of the moon. When this shock wave converged at the antipode, on the far side, it created a region of intense, localized heating, and perhaps even melting of the crustal rock. As this rock then cooled and solidified, in the presence of the Moon's ancient global magnetic field, it became strongly and permanently magnetized. The impact, in a sense, acted as a cosmic recording head, imprinting the signature of the global magnetic field onto the crustal rock at its antipode. And these ancient magnetic memories are not the only strange and beautiful feature of the lunar surface. There are also the lunar swirls, strange, sinuous, and bright patterns that are found in several locations on the Moon. These swirls are not associated with any topographic features. They are like delicate and ghostly paintings on the lunar regolith. And they are almost always found in regions of strong, localized magnetic anomalies. The leading theory is that these magnetic anomalies are acting as miniature and very weak magnetospheres, shielding the surface from the constant, darkening effect of the solar wind, and thus preserving the brighter, more pristine appearance of the underlying soil. The lunar swirls are a direct and beautiful visual manifestation of the Moon's hidden and fossilized magnetic past, the story of the Moon. As revealed by our decades-long and still ongoing scientific exploration, is a story of profound and beautiful asymmetry. It is a tale of two very different worlds bound together in a single celestial body. The near side is a world of dramatic contrasts, of dark, volcanic Maria and bright, ancient highlands, a world whose face has been shaped and reshaped by a long and complex history of both internal geological activity and external cosmic bombardment. The far side is a more ancient, more uniform, and in many ways a more honest world, a world that has been largely spared from the resurfacing effects of volcanism, a world that has preserved, with a stark and beautiful clarity, the deep and violent scars of its own primordial past. This fundamental dichotomy is not just skin deep. It is a reflection of a deep and enduring asymmetry in the Moon's very structure, in the thickness of its crust, in the distribution of its internal heat, and in the fossilized remnants of its ancient magnetic field. And it is a story that has been painstakingly and beautifully pieced together by a long and heroic series of scientific missions that have taken us from our first, blurry and ghost-like glimpses of the hidden side to the detailed, high-resolution, and multifaceted understanding that we have today. The once hidden, far side of the Moon is no longer a blank page in our cosmic atlas. It is a rich and complex and beautiful new chapter, a chapter that is not just about the Moon, but about the deep, and often violent, history of our entire solar system, and about our own small and precious place within it. The journey to the Moon has not just been a journey to another world, it has also, and always, been a journey home. A journey that has given us a new and more profound appreciation for the beauty, the fragility, and the sheer cosmic good fortune of our own, blue and white, and very much alive, planet Earth.